How did the newborn universe transform from formless energy into stars, galaxies, and worlds? Why did Earth, among countless planets, become a cradle for life? Could the same cosmic conditions that birthed us be unfolding right now around distant suns? In the soft darkness of night, imagine gazing up at the endless tapestry of stars. Each faint point of light is a memory from a universe that is about 13.8 billion years old. A universe that in its earliest moments was unimaginably different from the cosmos we know. In those first instants, everything was compressed into a dense, hot sea of energy and particles, a state that defies everyday experience. There were no stars, no galaxies, and no atoms yet. Time and space themselves were just beginning to unfurl. This is the canvas upon which all cosmic stories begin. For a fleeting fraction of a second, this young universe underwent a rapid expansion. The theory of cosmic inflation describes an era when quantum fluctuations were stretched to cosmic scales, seeding the density variations that would later become galaxies. During this period, space itself expanded faster than the speed of light, smoothing out irregularities and setting the stage for the uniform cosmic microwave background radiation we observe today. Inflation turned the tiny, turbulent early universe into a vast expanse that would slowly cool and coalesce over billions of years. Imagine this as a breathless moment when the universe exhaled into being. As expansion continued, the universe remained a thick, opaque plasma of electrons and nuclei. Only when it cooled enough for electrons to combine with protons did neutral hydrogen atoms form, making the cosmos transparent for the first time. This transition allowed light to travel freely, leaving behind the cosmic microwave background, a faint afterglow that still bathes the universe in microwave radiation. It is as if the universe suddenly cleared its own fog, revealing a darkness lit by an ethereal glow. The patterns in this light tell us about the tiny fluctuations that would grow into vast structures. After the cosmic microwave background formed, the universe entered what astronomers call the Dark Age. With no stars to shine, space was filled with neutral hydrogen gas and subtle fluctuations in density. Over hundreds of millions of years, gravity amplified these variations, pulling gas into clouds that eventually collapsed under their own weight. In these collapsing clouds, the first stars ignited, bringing light to the cosmos for the first time since the Big Bang. It was a long wait, but the darkness held the promise of starlight. The first generation of stars, called Population 3 stars, were very different from the stars we see now. They formed from pure hydrogen and helium, lacking heavier elements, and were likely hundreds of times more massive than our Sun. Such enormous mass meant they burned hot and fast, living brief, brilliant lives before exploding as supernovae. In their violent deaths, they created and dispersed heavier elements like carbon and oxygen into space, enriching their surroundings. These early beacons also left behind black holes that may have become the seeds for the supermassive black holes we find at galactic centers. With the first stars came the birth of galaxies. Over time, galaxies drew together into a vast cosmic web, with filaments of stars and gas stretching across space. Star formation surged as galaxies merged and gas flowed into dense regions. The cosmic star formation rate climbed to its peak roughly 10 to 11 billion years ago and has been declining ever since. Today, only a few % of stars are born compared to that early peak, and the universe has completed most of its star-making. The ebbing of this cosmic tide has shaped the distribution and composition of stars we see. At its height, star formation was prolific. By about 12.9 billion years after the Big Bang, an estimated 98% of all stars had already formed. 3/4 of the stars we see today were born by the time the universe was about 6.5 billion years old, and half had appeared by around 4.9 billion years. This frenetic pace slowed as galaxies used up their gas and the universe expanded, making it harder for gas to collapse into new stars. The majority of stars in the night sky are ancient, witnesses to a time when star birth was a cosmic frenzy. Our Sun, by contrast, emerged relatively late in this story. Galaxies themselves were dynamic in their youth. During the universe's first few billion years, small protogalaxies merged frequently, fueling bursts of star formation and building up larger structures. Minor mergers, where a smaller galaxy was absorbed by a larger one, stirred gas and triggered new stars without destroying the spiral structure of the host. Major mergers, involving galaxies of comparable size, were rarer and more disruptive. They could transform graceful disks into elliptical forms and unleash starbursts. This cosmic dance shaped the diversity of galaxies we observe and influenced where and when stars formed. Our own Milky Way had humble origins. The earliest fragments that would become our galaxy took shape about 200 to 250 million years after the Big Bang, as star clusters condensed from primordial gas. These early clusters quickly enriched their surroundings with heavier elements, enabling subsequent generations of stars to form. Over the next few billion years, the Milky Way grew by gobbling up smaller companions and drawing in gas along filaments of the cosmic web. Through this gradual accretion and occasional minor mergers, a majestic spiral disk emerged. The galaxy we call home is a product of countless ancient interactions. One of the reasons our galaxy retains its spiral arms is that it has avoided catastrophic collisions. Major mergers can destroy disks, turning them into amorphous ellipses. Minor mergers, on the other hand, stir the disk but preserve its overall shape. The Milky Way has experienced mainly minor mergers, allowing it to remain a spiral galaxy with ongoing star formation. By contrast, the neighbouring Andromeda galaxy bears evidence of a past major merger, which may explain differences in its structure. Our galaxy's relatively peaceful history has given it time to develop complex structures and nurture star formation over billions of years. By the time the universe was about 9 billion years old, the cosmic environment had changed. The star-making gas supply had dwindled, and the remaining gas was enriched with heavier elements. It was during this quieter era that our solar system emerged. About 4.6 billion years ago, a cloud of gas and dust in the Milky Way's disk collapsed under its own gravity, possibly triggered by a nearby supernova shockwave. As the cloud shrank, it flattened into a spinning disk, with most of the material drawn to the center to form a new star. In the heart of this disk, the Sun was born when the pressure and temperature ignited hydrogen fusion. The newborn Sun shone warmly, surrounded by a swirling disk of leftover gas and dust. Over millions of years, particles in this disk stuck together, gradually building up into planets. Near the Sun, heat drove away lighter materials, so rocky worlds with iron cores formed. Farther out, ices could survive, allowing gas giants and icy planets to accumulate. Leftover fragments became comets and asteroids, relics of planet formation that still roam the solar system. Our planet, Earth, took shape in this cosmic construction zone, orbiting at a comfortable distance where conditions were neither too hot nor too cold. It was, by cosmic standards, a rare combination of circumstances. A key factor in Earth's suitability for life is its position within the Sun's habitable zone, sometimes called the Goldilocks zone. This is the range of distances from a star where liquid water can exist on a planet's surface. For hotter, more luminous stars, this zone is wider and farther out. For cooler red dwarfs, it is narrow and close in, exposing any planets to intense radiation. Every star has its own habitable zone, determined by its brightness and temperature. Earth happens to reside near the middle of our Sun's Goldilocks zone, where water can remain liquid and stable over long periods. This simple requirement is critical for life as we know it. At the same time, habitable zones are not static. As stars age, they brighten, and their zones shift outward. Our Sun has been slowly warming since its birth, and over hundreds of millions of years, the boundaries of its habitable zone have moved. Planets orbiting close to a star may find themselves too hot as the star ages, while those farther out may become temperate. In the case of red dwarfs, planets in the narrow habitable zone might be tidally locked, with one side perpetually facing the star and the other in darkness. Habitable zones thus set the stage, but planetary characteristics and stellar evolution determine whether life can persist. Beyond our solar system, astronomers have discovered thousands of exoplanets, many located within their stars' habitable zones. Some orbit stars like our Sun, while others circle cooler dwarfs or more massive stars. The diversity of these worlds suggests that the ingredients for life may be widespread. Yet, habitability depends on more than just distance from a star. A planet's atmosphere, magnetic field, and geological activity all play roles in maintaining surface water and regulating climate. Still, the concept of the Goldilocks zone allows us to imagine countless planets where water might flow and life might take hold, scattered across the galaxy. Earth's early history was tumultuous. Our planet coalesced from countless impacts, and it likely experienced collisions with other protoplanets, including the giant impact that formed the Moon. Despite this violence, Earth stabilized and, by around 4.3 billion years ago, may have developed conditions suitable for life. The oldest known fossils, simple microbial structures, date back about 3.7 billion years. There is evidence that life might have emerged multiple times during a 600 million year window, only to be wiped out by large impacts before taking root. Eventually, life persevered, seeding the planet with microorganisms in oceans, lagoons, and perhaps deep within rocks. Where exactly life began remains a topic of debate. Some scientists favor hydrothermal vents on the ocean floor, where hot, mineral-rich water creates chemical gradients that could foster the first metabolic reactions. Others point to warm little ponds, volcanic settings, or even interstellar chemistry as sources of prebiotic compounds. Regardless of the location, early Earth offered a variety of energy sources, from sunlight to volcanic heat, that could have driven the synthesis of complex organic molecules. Life's emergence appears to be tied to the planet's ability to maintain liquid water and stable environments over long periods. For the first few billion years, life remained simple. Microbial mats and single-celled organisms dominated the planet, quietly shaping the atmosphere and environment. They produced oxygen through photosynthesis, gradually transforming Earth's atmosphere from a reducing mix to the oxygen-rich air we breathe. Complexity took a long time to develop. The emergence of sexual reproduction, multicellularity, and specialized cell types enabled organisms to grow larger and diversify. Around 550 million years ago, during the Cambrian explosion, a remarkable burst of evolutionary creativity occurred, filling the oceans with diverse animals, plants, and fungi. Even then, It had taken nearly 4 billion years for macroscopic life to flourish on Earth. Why did complexity take so long? Part of the answer lies in chance events and environmental stability. Earth needed to maintain a stable climate for hundreds of millions of years to allow complex life to evolve. Yet it also required periodic challenges to drive adaptation. Large-scale ice ages, volcanic eruptions, and asteroid impacts repeatedly reshaped ecosystems. The transition to multicellular life may have depended on innovations like eukaryotic cells and symbiosis. Because of these contingencies, it remains uncertain whether complex life is common in the universe or an exceptionally rare outcome. On some worlds, life may never progress beyond microbial simplicity. As life diversified on Earth, it altered the planet itself. Plants colonized land, increasing oxygen levels and stabilizing soils. Animals evolved complex nervous systems, and ecosystems grew richer. Human beings, appearing very recently in this long history, have further transformed the planet, shaping landscapes and climate. Yet, we occupy only a tiny fraction of geological time. The window for complex life on Earth is limited. The sun continues to brighten, and in about 1.3 billion years, rising temperatures will likely evaporate the oceans and strip away much of the atmosphere. By the time the sun swells into a red giant, Earth will be long uninhabitable. This limited window underscores the delicate balance required for complex life. It took nearly 4 billion years for animals and plants to appear, and they may last only a fraction of that time before conditions become hostile. Stars more massive than the sun burn faster and offer even narrower windows, while smaller stars, though long-lived, often emit flares and intense radiation. Planets must also maintain magnetic fields, plate tectonics, and active geologic cycles to recycle nutrients and prevent atmospheric loss. These requirements suggest that the emergence of complex ecosystems might be constrained to particular cosmic epochs and environments. The cosmic timeline makes the idea of ancient civilizations both plausible and poignant. The universe is far older than Earth, and many stars and planets formed long before the sun. If life can arise elsewhere, some worlds could have nurtured civilizations billions of years before we evolved. Such civilizations would have had vast amounts of time to grow, flourish, and perhaps decline. In the grand sweep of cosmic time, a million years is a heartbeat. Civilizations could rise, explore, leave traces, and vanish without overlapping with ours. The silence we experience today may be due to this staggering time gap. Astronomers estimate that there are hundreds of billions of stars in our galaxy, and many may host planets within their habitable zones. Some of these stars are billions of years older than the Sun, meaning their planets had more time for life to evolve. The Fermi paradox arises from the seeming contradiction that in such a vast, old galaxy, intelligent life should be common, yet we have not detected any unambiguous signs. Possible resolutions include the rarity of life, the challenge of interstellar travel, and the tendency of civilizations to self-destruct or avoid broadcasting signals. Another possibility is that they are simply too far away or too fleeting for us to detect. Distance itself poses a profound challenge. Signals weaken over light years, and the cosmic speed limit makes communication across the galaxy slow. Even if a civilization broadcast radio waves, by the time those waves reached us, the originators might no longer exist. We also might not be listening at the right frequencies, or our technology may be unable to recognize alien transmissions. Some civilizations may choose to remain silent, hiding from potential threats. Others might exist in forms we cannot easily detect, such as machine intelligences inhabiting interstellar clouds. Silence does not imply emptiness. It may reflect the limits of our perception. The concept of ancient civilizations invites us to contemplate deep time. For billions of years before humans walked the earth, stars shone and galaxies whirled. Planetary systems formed. Life may have taken root, and entire biospheres could have evolved and perished. Our species has existed for only a blink of an eye on this timeline. Looking ahead, it is likely that Earth will remain habitable for another billion years. But eventually, it will succumb to the sun's changes. The universe will continue, perhaps supporting new forms of life elsewhere, long after the last human has gone. As we ponder cosmic history, we also recognize our ability to perceive it. Our tools and telescopes allow us to look billions of years into the past, capturing light that has traveled across time. The cosmic microwave background offers a snapshot of the universe when it was only 380,000 years old. Observations of distant galaxies let us witness their youth. Through chemical analyses, we infer the enrichment of elements by successive generations of stars. Each measurement helps us piece together our cosmic ancestry and understand how galaxies, stars, and planets came to be. In this story, heavy elements play a starring role. The first stars forged simple atoms into carbon, oxygen, and iron, then spread them through space when they died. Subsequent generations of stars incorporated these elements, forming planets with rocky surfaces and atmospheres. Without these early, massive stars, there would be no planets like Earth. The slow build-up of heavy elements over time sets a cosmic schedule for when rocky worlds can form. This is one reason why our Sun, born after billions of years of star formation, was able to host such a diverse planetary system. The decline in star formation also affects the prospects for life. When the universe was young and star formation was rampant, massive stars lived short, violent lives, bathing galaxies in intense radiation. It may have been too harsh for complex life to develop. As star formation slowed, calmer conditions prevailed, creating long-lived, stable environments where life could persist. We may be living in a sweet spot of cosmic time, when enough heavy elements exist to build habitable planets, but there is still enough activity to nurture them. The future will see fewer new stars, and perhaps fewer chances for life to emerge. Galactic environment matters as well. Our solar system orbits in a relatively quiet part of the Milky Way, far from the crowded central regions where supernovae and black holes reside. This location shields us from lethal radiation events and gravitational disturbances that could disrupt planetary orbits. Throughout the galaxy, habitable zones within galaxies themselves may exist, where the balance between heavy element abundance and safety from catastrophic events is favorable. Planets too close to the galactic center may be bombarded by energetic explosions, while those too far out may lack the elements necessary for life. In thinking about ancient civilizations, we must also consider technological longevity. Advanced societies might have harnessed energy from their stars or traveled across interstellar distances. They may have left artifacts or signals that persist, but over millions of years, even monumental structures can erode, and signals can fade into noise. A spacecraft traveling between stars could be lost in the vastness of space. Even if traces remain, our ability to detect them is limited by our instruments and knowledge. Searching for ancient civilizations is like reading a palimpsest written in faint ink across the fabric of space-time. Some theorists suggest that civilizations could transition to forms we would not recognize. They might upload consciousness into artificial platforms or merge with technology, existing within digital realms or energy patterns. Such beings might not require planets, or may prefer environments we consider inhospitable. Others propose that advanced civilizations would master resources at the scale of their star, building megastructures like Dyson spheres to capture energy. If such structures exist, they might be detectable by the unusual infrared signatures they produce, but no conclusive evidence has been found to date. The absence of clear signs of alien civilizations does not mean they never existed. Civilizations may be transient, rising and falling in cycles. They could succumb to cosmic catastrophes, environmental collapse, or self-inflicted disasters. Their moment of visibility may have passed long ago, their achievements now swallowed by time. Alternatively, life may be scarce, and we may be among the first. The Fermi paradox encourages humility. The universe does not owe us contact. Whether we are alone or one among many, our curiosity drives us to search. Looking back on Earth's story, we see multiple extinction events that nearly reset life. The Permian-Triassic extinction wiped out most marine species and reshaped life on land. The asteroid impact that ended the dinosaurs allowed mammals to flourish. Each catastrophe opened new ecological niches and spurred evolution. Civilizations, too, may face crises that determine whether they persist or vanish. Understanding how life adapts and survives can provide insights into the resilience of hypothetical alien societies. Earth's plate tectonics and magnetic field are vital for maintaining habitable conditions. The movement of plates recycles carbon and stabilizes the climate, while the magnetic field shields the surface from charged particles. Worlds lacking these features may struggle to sustain life over geologic times. Mars, for example, lost its global magnetic field early and subsequently lost much of its atmosphere. Venus's dense atmosphere and lack of plate tectonics create a runaway greenhouse effect. These examples highlight how delicate the balance is for long-term habitability. Our perspective on time is shaped by our brief lifespans. A human life is measured in decades, while a civilization may last centuries or millennia. Geological processes unfold over millions of years, and cosmic events span billions. Contemplating ancient civilizations requires us to stretch our imagination across these scales. 1 billion years is enough time for species to evolve, planets to change, and stars to die. If civilizations arise, they could have multiple chances to expand and adapt. Alternatively, they might find stability and choose to remain local, exploring inner worlds of consciousness rather than the outer cosmos. The cosmic microwave background, the afterglow of the early universe, will continue to fade as the universe expands. In trillions of years, when the last stars die, the universe will enter a dark era. In that distant future, only degenerate remnants, white dwarfs, neutron stars, and black holes will remain. If civilizations exist then, they may rely on exotic energy sources and exotic physics. However, such speculative futures underscore the importance of the present. We live in an epoch rich with starlight, complexity, and potential. Our actions today might influence the cosmic legacy we leave. As we trace the cosmic story, the interplay of physics, chemistry, and biology becomes apparent. Inflation set the initial conditions, while nucleosynthesis in stars forged elements, planetary processes shaped environments, and chemical reactions gave rise to life. Evolution and natural selection steered life's trajectory on Earth, leading to intelligent beings capable of reflecting on their origins. This chain of events is contingent and delicate, making us appreciate how many things had to go right for our existence. There is also a philosophical dimension to imagining ancient civilizations. It invites us to question our significance and our responsibilities. If we are alone, then preserving and expanding life becomes our unique task. If we are not alone, we become part of a cosmic community, even if we never meet our neighbors. Either scenario carries weight. Recognizing the fragility and rarity of life may inspire us to protect our planet and cherish the moment we inhabit. In considering ancient civilizations, we must guard against anthropocentrism. Other intelligences might not develop technology as we understand it. They might communicate through chemical signals, bioelectric pulses, or quantum phenomena. Their societies might be fluid networks, rather than hierarchical structures. They could dwell in oceans, ice shells, gas clouds, or even the atmospheres of giant planets. Our search strategies must be broad and imaginative, accounting for possibilities beyond human experience. Science provides tools to explore these ideas. Radio telescopes scan the sky for artificial signals, while optical observatories look for unusual light patterns. Space missions investigate planets and moons within our solar system, searching for microbial life. The discovery of even simple life elsewhere would transform our understanding of the universe. It would demonstrate that life is not unique to Earth, and that the cosmos may be teeming with potential. Finding evidence of ancient technological relics would be even more profound, confirming that we share the universe with other intelligences. Our own technological footprint may be detectable to distant observers. Radio and television broadcasts have been leaking into space for decades, though they fade quickly. Our planet's atmosphere bears signatures of industrial activity. Bright city lights could appear as odd patterns on the night side to sophisticated instruments. If civilizations monitor planets for biosignatures and technosignatures, they might classify Earth as a world undergoing technological transition. In that case, we have already announced our presence without intending to. As we search, we must also consider that we might not recognize what we find. Complex patterns in fast radio bursts, neutrino fluxes, or gravitational waves could be artificial, but we currently attribute them to natural sources. Our understanding of physics and technology is incomplete. A sufficiently advanced civilization may manipulate matter and energy in ways that are indistinguishable from natural processes. The line between natural and artificial may blur, making detection challenging. Despite these challenges, the question of ancient civilizations continues to fascinate. It taps into our sense of wonder and curiosity about the universe. Contemplating civilizations that rose and fell long ago adds depth to the cosmos, transforming it from a silent expanse into a potential tapestry of stories. Whether these stories exist or not, the very act of pondering them connects us to the cosmos and to each other. It is also possible that civilizations avoid leaving traces. They might value sustainability and choose not to extract energy on large scales. They might live harmoniously with their environments, leaving little impact beyond their immediate ecosystems. Such cultures would be difficult to detect from afar. In this scenario, the absence of evidence reflects an ethic of cosmic discretion. Civilizations could thrive quietly without altering the broader galactic landscape. Another intriguing possibility is that life evolves in cycles tied to cosmic conditions. During periods of intense star formation, radiation may suppress complex life. As the universe quiets, windows open for life to emerge, flourish, and perhaps spread. Eventually, resources diminish and environments change, leading to declines. These cycles could repeat, producing waves of life and intelligence across billions of years. Our epoch might represent one such wave, with future epochs yet to come. Time also allows for transformation. Planetary systems can migrate, stars can exchange planets through gravitational interactions, and galaxies can collide. Over billions of years, a world that hosted life could be ejected into interstellar space or swallowed by its star. Civilizations may adapt by moving to new homes or by shifting to artificial habitats. The cosmic environment is dynamic, and survival may depend on flexibility and foresight. Considering our own future, humans are beginning to contemplate interplanetary and interstellar travel. Our technological progress has been rapid compared with geological timescales. We have gone from stone tools to exploring other planets in a fraction of a million years. If we survive and continue advancing, we could spread beyond Earth. This expansion could ensure the longevity of our species, but it also carries ethical questions about colonization, planetary protection, and the preservation of alien biospheres. Should we encounter life elsewhere, whether microbial or intelligent, we will face profound choices. How do we interact? Do we share knowledge, remain silent, or observe from a distance? The way we respond could influence our place in the cosmos and our understanding of ourselves. These considerations underscore the need for thoughtfulness and humility as we explore. The formation of habitable planets depends on cosmic chemical evolution. Heavy elements like carbon, nitrogen, oxygen, and phosphorus must be present in sufficient quantities. These elements are forged in stars and spread by supernovae and stellar winds. When new stars form, their planets inherit this material. Over time, the abundance of heavy elements has increased, making the formation of rocky, potentially habitable planets more common in later generations of stars. This timing may constrain when life can emerge and thrive. While star formation declines, red dwarf stars continue to form and will outlive stars like the Sun by trillions of years. These stars are small and cool, but they are prone to flaring. Planets orbiting them may face harsh radiation, but their long lifespans mean that if life can adapt, it could have an extraordinarily long time to evolve. Some speculate that the ultimate bastions of life in the far future could be around red dwarfs, thriving in environments very different from ours. The Milky Way is not static. It is on a collision course with Andromeda. In about 4 billion years, the two galaxies will merge in a grand dance. By then, the Sun will be nearing the end of its life, and Earth may already be uninhabitable. The merger will transform both galaxies, triggering new waves of star formation. It is possible that new habitable worlds will form in the aftermath, perhaps becoming homes to future life. Cosmic cycles of creation and destruction continue on grand scales. On a smaller scale, comets and asteroids deliver water and organics to young planets. These cosmic messengers may seed planets with the ingredients for life. Earth's oceans may have been filled in part by cometary impacts, and organic molecules have been detected on comets and meteorites. Such deliveries could be common throughout the galaxy, making the origins of life less improbable. Even so, the steps from chemistry to biology remain poorly understood and may depend on unique planetary environments. Life on Earth has adapted to extreme environments, from boiling hydrothermal vents to frozen Antarctic lakes. These extremophiles teach us that life can be resilient and versatile. On other worlds, life might survive in subglacial oceans beneath icy crusts, in the subsurface of Mars, or in the dense atmospheres of gas giants. Ancient civilizations could have arisen in places we consider hostile. Our search should encompass such environments and remain open to forms of life that differ from our expectations. Imagine a civilization that emerged on a planet orbiting a massive star. Its sun would burn brightly and quickly, offering only a brief window for evolution. The inhabitants might evolve rapidly, harness their star's energy efficiently, and perhaps leave their planet as it becomes uninhabitable. Their technology could be oriented towards survival in space, leaving little trace on their short-lived homeworld. By the time we look at their planet, the star might have died, leaving only a neutron star or black hole. Conversely, a civilization around a long-lived red dwarf might develop slowly, with ample time to refine its culture and technology. These beings could focus on sustainability, knowing they have trillions of years ahead. They might see no urgency to expand beyond their system, content with deep exploration of their own world. Their longevity could allow for a stable, ancient society that outlasts many cosmic events. Yet, the flaring nature of their star might pose ongoing challenges, shaping their biology and technology. The origin of life may also depend on planetary surface composition. For life as we know it, elements like phosphorus are essential for DNA and energy transfer. If a planet forms in a region of the galaxy with low phosphorus abundance, life may be constrained. The distribution of elements varies across the galaxy, reflecting the contributions of different generations of stars. Thus, not all regions may be equally fertile for life. Ancient civilizations might have arisen preferentially in chemically rich environments. Chemical evolution continues today. Stars still form, albeit slowly, and supernovae continue to enrich interstellar space. In the distant future, the interstellar medium may become depleted as material is locked into stellar remnants. The supply of raw materials for new planets will diminish. This points to a finite window for the formation of habitable planets. If ancient civilizations existed, they may have done so during a period when star formation and chemical enrichment were still robust. The story of life is intimately tied to energy flows. Life harnesses energy from light, chemical gradients, and heat. As the universe ages and stars die, available energy sources will change. Civilizations may adapt by tapping into black hole accretion disks, harnessing gravitational waves, or capturing the energy of dark matter annihilations. These ideas verge on speculation, but they highlight the creativity needed to survive in a changing cosmos. Our search for ancient civilizations is also a search for ourselves. By examining other worlds, we learn more about our own planet's history and future. Mars, with its dry riverbeds and ancient lakebeds, hints at a once habitable past. Europa and Enceladus, moons of Jupiter and Saturn, harbour subsurface oceans that could host life. Studying these worlds teaches us about habitability beyond Earth. If we find even microbial life, it would suggest that life can arise independently, increasing the likelihood that ancient civilizations could have emerged elsewhere. Listening for signals from the stars is a patient endeavour. Projects like SETI scan vast swathes of the sky, analysing radio waves for patterns that stand out from natural noise. Advances in technology allow us to process enormous amounts of data and identify faint signatures. However, the cosmic haystack is enormous, and our needles may be subtle. The search is a long-term commitment, driven by curiosity and the desire to answer one of humanity's oldest questions. Are we alone? In addition to radio searches, scientists look for technosignatures, indications of technology on a planetary scale. Such signatures could include unusual atmospheric gases, artificial lighting, or heat patterns consistent with large structures. Observatories like the James Webb Space Telescope can analyze exoplanet atmospheres for chemical disequilibrium that might indicate biological or technological activity. These methods open new windows into the possibility of ancient or current civilizations, though interpreting these signals requires caution. Our understanding of ancient civilizations is constrained by the limitations of our technology and our own imaginations. As instruments become more sensitive and our theoretical models more sophisticated, we may uncover evidence that challenges our assumptions. Interdisciplinary collaboration between astronomers, biologists, chemists, and philosophers enriches this pursuit. The search for ancient civilizations is as much about expanding human knowledge as it is about finding specific answers. In reflecting on cosmic history, we also confront the fragility of our own civilization. We face challenges such as climate change, resource depletion, and societal conflict. These issues test our ability to maintain a stable, technological society. Understanding that we inhabit a transient window of habitability may motivate us to act responsibly. If ancient civilizations elsewhere succumb to their own actions, their silence could serve as a warning. Conversely, the absence of detectable civilizations might imply that long-term sustainability is difficult to achieve. Civilizations may reach technological maturity and then collapse. Alternatively, they might intentionally limit their growth and remain invisible. In both cases, the lesson is to consider the long-term consequences of our choices. We have the ability to alter our planet's environment. We should choose wisely. Aspiring to be a cosmic neighbor also inspires optimism. If life is rare, our existence is precious, and spreading life beyond Earth becomes a noble goal. If life is common, contact with another civilization could enrich us in ways we cannot imagine. Even without direct contact, the knowledge that others exist would broaden our perspective. It would remind us that the universe is not indifferent, but filled with potential stories. The idea of ancient civilizations has influenced culture and art for centuries. Stories of Atlantis, lost cities, and ancient astronauts reflect a deep-seated fascination with forgotten worlds. In science fiction, writers imagine societies that harness stars, build vast structures, or transcend physical form. These narratives inspire scientific inquiry and invite us to consider possibilities beyond our current reality. They also serve as cautionary tales, illustrating the impermanence of even the most advanced societies. Contemplating deep time can evoke feelings of both insignificance and wonder. On one hand, the vastness of cosmic history dwarfs our individual lives. On the other, our ability to understand and imagine this history is a remarkable achievement. Each of us, for a moment, participates in a cosmic dialogue that spans billions of years. This awareness can instill humility and gratitude, prompting us to appreciate the beauty and complexity of the universe. At the core of these musings is a simple truth. The universe is an ongoing experiment. Matter and energy interact, form structures, and occasionally give rise to life. Life, in turn, evolves and sometimes develops consciousness. Civilizations may emerge, reflect on their origins, and wonder about their neighbors. The cycle continues, driven by the interplay of physical laws and chance. Whether ancient civilizations have existed or not, the possibility enriches our understanding of what the universe can be. Our journey through cosmic history reveals patterns of emergence and decline, of creation and dissolution. Stars ignite and die, galaxies collide and merge, Planets form and erode. Life arises, evolves, and sometimes perishes. Civilizations may follow similar trajectories. Recognizing these patterns helps us place ourselves within the cosmic story. It encourages us to consider how we might endure and what legacy we want to leave. Despite the grandeur of cosmic timescales, the essence of life is often found in small moments and simple interactions. The first cells dividing, the first animals crawling onto land, the first human gazing at the stars. All are steps in a larger narrative. Ancient civilizations, if they existed, likely had their own seminal moments. They may have built their first cities, discovered their first principles of physics, or created art that spoke to their hearts. These experiences resonate across time and species. Understanding cosmic history also deepens our appreciation of the natural world. The carbon in our bodies was forged in ancient stars. The water we drink may contain hydrogen, formed in the first 3 minutes after the Big Bang. The calcium in our bones came from long-dead supernovas. We are, quite literally, made of the universe. This connection binds us to the cosmos and underscores the unity of all things. As we think about ancient civilizations, we might also ponder how they would perceive the universe. Would they view their world as unique? Or would they assume others exist? Would they explore their surroundings or focus inward? The answers could vary widely, shaped by culture, biology, and environment. Our own perspective is one among many possible ways to engage with the cosmos. Perhaps ancient civilizations faced their own Fermi paradoxes. They may have looked up at their night skies, wondered if they were alone, and debated the likelihood of others. The silence they experienced could have influenced their philosophies and priorities. Like us, they might have built observatories, developed theories, and dreamed of contact. Their contemplation would add another layer to the tapestry of cosmic curiosity. The search for ancient civilizations is ultimately a search for meaning. It compels us to ask why we are here and what we might become. It challenges us to extend our vision beyond the immediacy of daily life and to consider our place in a vast, dynamic universe. Whether or not we ever find evidence of ancient civilizations, the questions they inspire enrich our understanding of ourselves and the cosmos. In this narrative, the early universe provides the backdrop, star formation and galactic evolution lay the foundation, and the emergence of the solar system sets the stage. Life's origins and evolution on Earth illustrate the delicate dance of chemistry and time. The idea of ancient civilizations invites us to imagine what could have been and what might still be. Together, these elements weave a story that is both scientific and poetic, grounded in evidence yet open to wonder. Looking forward, our exploration continues. The next chapters of this story might include discoveries of biosignatures on exoplanets, detection of technosignatures, or even signs of ancient artifacts. Our understanding will evolve as new data arrives and theories develop. We stand at a threshold where knowledge meets imagination and where curiosity propels us into the unknown. The universe beckons, and we are eager to listen. As we embark on the next part of our journey, remember that the cosmos is vast and full of mysteries. The possibility of ancient civilizations is one such mystery, tantalizing and profound. Whether we find evidence or not, the search itself enriches us, encouraging patience, persistence, and open-mindedness. We learn not only about the universe, but about our own capacity to seek and wonder. With each observation, each experiment, and each thought, We contribute to a collective human endeavor that transcends borders and generations. We are part of a continuum of explorers who have looked to the heavens for answers. Our quest connects us to ancient astronomers who charted the stars and to future scientists who will probe deeper. The cosmos remains a shared heritage, inviting us to participate. In pondering ancient civilizations, we also confront the fleeting nature of our existence. Our lives are brief, yet we have the ability to impact the future. The choices we make today, from preserving the environment to exploring space, will shape what stories can be told tomorrow. Perhaps, in some distant future, another civilization will gaze at the stars and wonder about us. What will our legacy be? Our narrative pauses here, not with a conclusion, but with anticipation. We have traced the universe from its fiery birth to the emergence of life and the potential for civilizations. The next part of our journey will continue this exploration, delving deeper into the possibilities of ancient societies and the evidence we might seek. The cosmos unfolds slowly, and our curiosity is infinite. Let us continue to dream and to learn, guided by the starlight that has illuminated our path since the dawn of time. The history of cosmic expansion shows that space itself stretches, carrying galaxies apart. Over the past billions of years, the accelerating expansion, driven by dark energy, has diluted matter, making interactions between galaxies less frequent. In the future, this expansion may isolate galaxy groups, creating cosmic islands. Ancient civilizations could have lived in a universe where galaxies were closer together, making intergalactic travel easier. Today, we reside in a widening cosmos, where the night sky remains mostly unchanged over human lifetimes. Throughout the Dark Age and the subsequent periods, gravity sculpted the universe. Tiny fluctuations amplified, forming filaments and voids that define the cosmic web. This structure guided the flow of gas and the formation of galaxies. The cosmic web is like a skeleton upon which the universe built its large-scale architecture. It also influenced where life-sustaining elements accumulated. Understanding this framework helps us grasp the environment in which civilizations might arise and how they might move through space. Observing extremely distant galaxies provides glimpses into the cosmic dawn. Instruments like the James Webb Space Telescope have revealed galaxies that existed only a few 100 million years after the Big Bang. These young galaxies are clumpy and irregular, rapidly forming stars and merging. They represent the early stages of galaxy evolution, before the settled disks and ellipticals we see today. The light from these distant objects traveled billions of years to reach us, carrying messages from a time when the universe was young and energetic. In the early universe, heavy elements were scarce, so rocky planets like Earth could not form. As generations of stars lived and died, metals accumulated, enabling the creation of solid cores and atmospheres. This chemical enrichment took time, suggesting that the earliest potential for life may have been delayed until the universe was a few billion years old. Ancient civilizations, if they existed, likely arose well after the first stars, but still long before the present. Our understanding of these timelines helps us estimate when and where civilizations could emerge. The concept of a galactic habitable zone parallels the idea of a stellar habitable zone. It refers to regions within a galaxy where conditions favor life. Too close to the galactic center, radiation and gravitational disturbances are intense. Too far out, there may be insufficient heavy elements. The Milky Way's habitable zone lies roughly between about 7,000 and 9,000 light-years from the center. Our solar system sits within this region. Ancient civilizations might have clustered in similar zones, where the balance between safety and resources was optimal. While we often imagine civilizations on planets, moons could also host life. In our solar system, moons like Europa and Enceladus hide oceans beneath icy crusts. Tidal heating keeps these oceans liquid, independent of distance from the sun. If life arises there, it would be shielded from space and potentially long-lived. Ancient civilizations could have evolved under ice, using chemosynthesis rather than photosynthesis. Their existence would challenge our assumptions about the environments that nurture intelligence. Another factor influencing civilizations is planetary rotation and axial tilt. Earth's tilted axis gives us seasons, which drive ecological cycles and evolutionary pressures. A planet with no tilt might have less seasonal variation, potentially affecting the development of life. A tidally locked planet presents one hemisphere perpetually to its star, creating a stark day-night divide. In such worlds, civilizations might adapt to the twilight zone between the hot and cold hemispheres. Each planetary configuration presents unique challenges and opportunities. Cosmic rays and radiation events can influence habitability. Supernova explosions and gamma-ray bursts can strip away atmospheres or trigger mass extinctions. The frequency of these events depends on a planet's location within its galaxy. Ancient civilizations might have experienced and adapted to such threats. Their history could include myths and technologies developed in response to cosmic hazards. Studying cosmic ray histories helps us appreciate the environmental pressures that shape life. Timescales for technological development could vary widely. On Earth, technology accelerated rapidly once humans emerged. But in other societies, cultural choices or environmental constraints might slow or speed progress. A civilization with abundant resources might achieve space travel quickly, while one on a water world might advance differently. The idea of ancient civilizations prompts us to consider these diverse trajectories. It teaches us that intelligence does not necessarily lead to the same outcomes everywhere. Finally, the transition from single-celled to multicellular life on Earth was a watershed moment that required cooperation among cells. This cooperation is mirrored in civilizations, where individuals work together to build structures, share knowledge, and pursue goals. The success and longevity of civilizations depend on cooperation and the management of shared resources. Ancient civilizations may have discovered this balance or failed to maintain it. As we end this part of our journey, we carry forward the notion that cooperation across time and space may be essential for any civilization to endure. His story picks up with a quiet revolution unfolding beyond the edges of our own solar system. Astronomers have confirmed the existence of over 6,000 worlds orbiting other stars, with thousands more candidates awaiting validation. Each discovery whispers that planets outnumber stars, transforming the night sky into a sea of potential homes. In the soft glow of twilight, we begin to understand that our cosmos is not barren, but richly adorned with countless unseen worlds. Not long ago, the idea of a planet beyond our neighborhood existed mainly in stories and speculation. The first hints came from tiny wobbles in the light of distant stars, suggesting unseen companions tugging at their suns. Those early detections demanded patience and skepticism, yet they opened a window onto a multitude of possibilities. Slowly, the catalogue of worlds grew, carrying our imaginations farther than we once thought possible. To sense a planet so far away, astronomers measure how a star's light dims as a world passes in front, or how the star subtly sways under the gravitational pull of an unseen companion. The transit method captures these fleeting shadows, while radial velocity tracks the stars' gentle dance. Direct imaging, the dream of seeing another world as a tiny point of light, remains rare because planets are faint compared to the brilliance of their suns. Fewer than 100 exoplanets have been directly photographed so far, and each image feels like a treasure. As the list grew, so did the range of worlds it contained. Some are rocky like our own planet, baked under bright suns or covered in endless ice. Others are giant balls of gas bigger than Jupiter, with orbits so tight that a year lasts only days, their surfaces glowing like molten lava. We have found planets circling two stars, worlds that wander between stars without a sun, and planets with densities as airy as styrofoam, or atmospheres that might rain gemstones. By carefully counting, astronomers now believe that there are more planets than stars in our galaxy. Every pinprick of light you see in the night might be circled by a family of worlds. This realization invites a sense of abundance that was once absent from our view of the universe. The Milky Way transforms from a sparse desert to a vast orchard, and we are only beginning to explore its harvest. Beyond the confirmed planets lies an even larger list of candidates awaiting confirmation. These signals hint at worlds whose existence is probable yet unproven, numbering in the thousands. Each one awaits further observations and careful analysis before joining the cosmic census. The sheer volume of possibilities hints that the 6,000 confirmed planets are only a small fraction of what is out there. Among these findings are the so-called hot Jupiters, gas giants orbiting so close to their stars that they complete a lap in mere days. Their atmospheres may be scorched and transformed into swirling seas of vaporized rock, painting scenes we can only imagine. These strange giants challenge our theories of planet formation, revealing that nature delights in diversity. They remind us that our own solar system's arrangement is but one possibility among countless others. We have also discovered planets that circle two suns, bathing in the combined light of a pair of stars, like the twin sunset in a familiar science fiction tale. Others have been flung from their home systems to wander the galaxy alone, free-floating in cold darkness. Such rogue planets demonstrate that the universe can be both generous and unforgiving, scattering worlds like seeds on the cosmic wind. They roam through interstellar space as silent voyagers, carrying unknown histories. The extremes of exoplanets defy easy categorization. Some are thought to be lava planets, with surfaces of molten rock glowing under unrelenting heat. Others are so fluffy that their densities are less than that of water, making them huge spheres of gas that could float in a cosmic ocean. Astronomers even speculate about worlds where the atmosphere contains clouds of exotic materials, perhaps raining rubies or sapphires in storms we can barely fathom. Every new discovery encourages our curiosity to wander further. Seeing these distant worlds directly is an ongoing challenge. A planet is faint compared to the star it orbits, and the glare from the star can overwhelm our instruments. The Sun is about 10 billion times brighter than Earth, and that ratio illustrates how difficult it is to spot a small, dim world near a blazing light. Advanced coronagraphs and clever techniques are slowly turning the tide, allowing us to glimpse exoplanets that once remained hidden. The transit and radial velocity methods complement each other beautifully. When a planet passes in front of its star, we measure the dip in brightness to determine its size, while the star's wobble reveals the planet's mass. Together, these measurements let us infer density and composition and refine our understanding of an alien world. Each technique adds a piece to a puzzle that grows more intricate with every discovery. Confirmation of a planet requires multiple observations and sometimes years of patience. False positives can arise from stellar activity or instrumental noise, so astronomers cross-check signals and apply rigorous tests. The process illustrates the careful nature of science, where enthusiasm is tempered by skepticism and verification. When a candidate is confirmed, it becomes a new bead on a vast necklace of worlds. This explosion in knowledge has transformed our perspective. For centuries, we suspected other planets existed, but now we know they are commonplace. The cosmic loneliness we once felt is softened by the thought of countless worlds orbiting countless suns. This quiet shift invites humility and a gentle realization that our own story is but one thread in a tapestry of unfathomable scale. The diversity of exoplanets invites us to imagine life under conditions very different from Earth's. Could organisms thrive on a world of endless daylight or in the twilight zone of a tidally locked planet? Might life adapt to an atmosphere thick with hydrocarbons or a landscape coated in diamond dust? Each possibility stretches our understanding of what living systems could be, prompting both scientists and storytellers to think creatively. The catalogue we have assembled is still young. Many of the planets we know about are large and orbit close to their stars, because those are the easiest to detect. As techniques improve, smaller, more distant worlds will come into focus. The sense of standing at the beginning of a much longer journey permeates the field, and researchers speak with excitement about what remains unseen. Exoplanets orbit stars of every kind, from cool red dwarfs that simmer quietly for trillions of years, to bright blue giants that blaze fiercely and die young. Some worlds circle remnants of stars, such as white dwarfs or pulsars, surviving cataclysmic explosions. This breadth of environments reveals the resilience of planetary formation, showing that worlds emerge wherever there is material and time. The cosmos seems to enjoy creating planets, scattering them widely. Some exoplanets reside within dense star clusters, their skies crowded with neighbouring suns that rise and set in dazzling numbers. Others orbit stars near the centres of galaxies, where gravitational forces from black holes and dense stellar populations create dynamic environments. These settings remind us that planets can endure in places we might not expect, adapting to gravitational tides and radiation storms. They expand our sense of where life might find a foothold. With each discovery comes a name and a story. Some names echo ancient mythologies, others honor telescopes or scientists, and still others simply follow catalogue numbers. In whispers and discussions, people ascribe personalities to these worlds, even though they are only points of data. This blending of rigorous observation and human imagination enriches the experience of exploration, making the distant tangible. The exoplanet revolution has driven technological innovation. Instruments sensitive enough to detect the minute dimming of a star and analyze the light of faraway worlds have been developed through decades of engineering. Space-based observatories operate far from Earth's atmosphere, while ground-based telescopes use adaptive optics to sharpen their view. Each leap in technology opens new doors, revealing details that were previously hidden in the glare. The pace of discovery continues to accelerate. New announcements arrive monthly, and the map of known planets stretches across the galaxy. Yet even this surge represents only a small fraction of what awaits. As we stand at the threshold of deeper exploration, we carry with us a sense of wonder and patience, knowing that the next decades will reveal worlds we have yet to imagine. The search for life focuses on worlds where liquid water can exist on the surface. This region, called the habitable zone, is where temperatures are neither too hot nor too cold. In our own solar system, Earth sits comfortably within this band, while Venus lies near the inner edge and Mars near the outer. The idea of a Goldilocks zone captures the delicate balance that fosters oceans, weather, and perhaps biology. Like the fairy tale, the Goldilocks region is about finding conditions that are just right. Move a planet too close to its sun, and its oceans boil away. Move it too far, and they freeze solid. Within the narrow band, liquid water can persist, enabling chemical reactions that are thought to be essential to life as we know it. The concept offers a simple guide for targeting promising worlds. The habitable zone varies with the star's brightness. Around dim red dwarfs, the zone hugs the star closely, while around bright stars it extends far out, covering distances greater than the orbit of Mars. This diversity means that each planetary system has its own Goldilocks ring, defined by the unique luminosity and spectrum of its sun. Astronomers map these zones carefully when evaluating new discoveries. Studies of Kepler data suggest that roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in its habitable zone. That proportion is astonishing when scaled to the hundreds of billions of stars in the Milky Way. It implies that our galaxy could be home to tens of billions of potentially temperate worlds. The nearest such planet might be only a dozen light-years away, within reach of our imagination. Yet being Earth-sized and in the habitable zone does not guarantee a pleasant climate. A planet may be shrouded in a thick atmosphere that traps heat, turning it into a runaway greenhouse like Venus. Alternatively, a thin atmosphere could leave its surface exposed to the cold vacuum of space. The study's authors caution that habitability depends on many factors beyond size and distance. The fraction of stars with temperate planets is estimated after correcting for observational biases. Our instruments favor finding large planets close to their suns, so scientists use statistical methods to infer what remains unseen. They consider how many small, distant worlds might be missed and adjust the numbers accordingly. This careful accounting gives confidence that the 1 in 5 figure is not just a lucky guess. Improving these estimates requires more data and more sophisticated models. Future missions will measure the frequency of planets of different sizes across a range of orbital distances. Machine learning and advanced simulations will help interpret the complex signals embedded in starlight. As we refine our techniques, the picture of habitable zones will become clearer, guiding the next generation of explorers. The inner edge of a star's habitable zone marks the point where a planet's surface would overheat due to the runaway greenhouse effect, while the outer edge marks the limit where carbon dioxide clouds could keep a world warm despite weaker sunlight. Between these boundaries lies a region where water can remain liquid across a planet's surface. The precise position of these edges depends on atmospheric composition and planetary rotation. Habitability is therefore a dance between distance, atmosphere, and the energy of a star. Life may also exist beyond the classic habitable zone. Bodies with subsurface oceans, such as Jupiter's moon Europa or Saturn's moon Enceladus, demonstrate that internal heating can sustain liquid water far from the sun. Exoplanets with similar internal energy sources could harbour vast oceans beneath ice crusts, hidden from view. These prospects widen the scope of habitability, reminding us not to limit our imagination to surface conditions alone. Planetary climate is shaped by more than just distance. Greenhouse gases like carbon dioxide and methane trap heat, while reflective clouds and ice send sunlight back into space. A world's rotation rate influences atmospheric circulation, distributing warmth and shaping weather patterns. Even the presence of a moon can stabilize a planet's tilt, preventing extreme seasons and promoting long-term climate stability. Worlds orbiting dim red dwarfs often become tidally locked, keeping the same face toward their star. One side bakes under permanent daylight, while the other languishes in eternal night, raising questions about whether such planets can host life. Some models suggest that a thick atmosphere or a deep ocean could transport heat from the day side to the night side, moderating temperatures. These possibilities illustrate the complexity of evaluating habitability. Red dwarfs are notorious for powerful stellar flares and intense ultraviolet radiation. These outbursts could strip away a planet's atmosphere or bathe its surface in harmful radiation. Life, if it arises, would need to adapt to such variable and harsh conditions. The dynamic environment around a red dwarf forces us to broaden our definition of what a habitable world might be. Our own planet's resilience hints that life might adapt to extremes elsewhere. Microorganisms on Earth survive in boiling hot springs, acidic lakes, and high radiation zones, suggesting that alien life could find a way under very different skies. Perhaps a biosphere could thrive beneath a thick veil of methane, or deep within a planet's crust. The habitable zone is a useful guide, but it may not be the only region where life can take hold. Giant planets may host moons large enough to sustain atmospheres and liquid water. In our solar system, some moons are nearly the size of planets, and their proximity to a giant host might provide tidal heating that keeps subsurface oceans warm. Around distant stars, such moons could exist in the habitable zone, bathing in both starlight and reflected light from their parent planet. Detecting exomoons remains a challenge, but their potential adds another layer to our search. There is also the possibility of life hidden underground. If a planet's surface is inhospitable, organisms might find refuge in caverns or under thick ice. Chemical energy from a planet's interior could feed ecosystems that never see starlight. Such speculation reminds us that habitability may be more about local conditions than simple distance from a star. The Goldilocks concept has captured public imagination because it offers a simple way to think about complicated planetary systems. It gives us a zone to aim for, a ring of warmth around each star where life might bloom. But beyond the science, it also invites us to dream about the diversity of climates and landscapes that could exist just beyond our reach. Wonder fuels the calculations, blending curiosity with methodical research. Stars change over time, and so do their habitable zones. As a star brightens over billions of years, the warm band moves outward, pushing once temperate planets toward uninhabitable heat. On longer timescales, some worlds might move into the zone as their star cools. The interplay between stellar evolution and planetary orbits means that habitability is not static. It ebbs and flows across cosmic eras. Even if only a small fraction of planets sit within their star's habitable zone, the sheer number of stars makes the potential count enormous. There are hundreds of billions of stars in the Milky Way, and perhaps 1 in 5 sun-like stars has a temperate, Earth-sized companion. This statistic yields an almost unimaginable number of possible abodes for life. It underscores why the search for habitable worlds is so compelling. The quest to find these Goldilocks planets is far from over. Astronomers plan new surveys to identify smaller and more distant planets, refining the census of temperate worlds. As instruments improve, we will begin to probe the atmospheres of these planets, looking for signs of water vapor or carbon dioxide. Each step brings us closer to understanding how common habitable environments truly are. Without drawing conclusions, the notion of habitable zones sets the stage for deeper exploration. It provides a scaffold for thinking about where life might emerge and thrive, while acknowledging that nature often surprises us. As we leave behind the abstract idea of Goldilocks circles, we turn our attention to specific nearby systems. One star system in particular beckons from just over 4 light-years away, promising both challenges and revelations. The nearest stellar neighbours to our Sun form a triple system known as Alpha Centauri. Two Sun-like stars, Alpha Centauri A and B, dance around each other, while a smaller red dwarf called Proxima Centauri circles at a greater distance. Their combined gravity shapes a complex environment where planets, if they exist, would experience multiple suns. To many dreamers, these stars represent the first steps on an interstellar journey. Because the system lies only a little over 4 light-years away, it has long fascinated both scientists and storytellers. If planets orbit these stars, they would be the closest possible destinations beyond our solar system. Ideas of interstellar probes or future human voyages often focus on this nearby beacon. The knowledge that our nearest neighbour might harbour worlds stirs a deep sense of anticipation. Detecting planets around Alpha Centauri A and B has proven particularly difficult. Their brilliance saturates most instruments, and their closeness to each other creates overlapping light that confuses detectors. Even small planets would be hidden in this glare, and specialized techniques are required to suppress the starlight. These challenges have made Alpha Centauri a proving ground for advanced planet-finding technology. Several years ago, a project using a special infrared instrument called NEAR, installed on the European Southern Observatory's Very Large Telescope, hinted at a possible planet around Alpha Centauri A. The candidate, labelled C1, was reported to be in the system's habitable zone, though the evidence was faint and uncertain. Follow-up observations were needed to confirm whether it was a real planet or a transient signal. The hint of C1 demonstrated how tantalizing and elusive these nearby worlds can be. Newer observations with the James Webb Space Telescope's mid-infrared instrument took this search further. By using a coronagraph to block the star's light, the telescope detected a faint source labelled S1 near Alpha Centauri A. The light was about 10,000 times fainter than the star itself, and located roughly twice the distance between Earth and the Sun. This detection offered a tantalizing hint of a planet in the system's habitable zone. The coronagraph works by placing a small mask over the star in the telescope's optics, suppressing its glare and allowing faint nearby objects to emerge from the background. In the Webb observations, multiple images were taken to ensure that the faint light was real and not an artifact. The detection of S1 in one observation, but not in others, suggested that the object might be moving along an orbit, or could be a statistical fluctuation. Such ambiguity is part of the frontier of exoplanet imaging. Simulations of the S1 signal suggest it could be a gas giant, with a mass similar to Saturn, in a highly elliptical orbit around Alpha Centauri A. If this interpretation is correct, the planet would pass through the habitable zone during part of its journey, though as a giant, it would not be habitable itself. The orbit might take it far from the star at times, and much closer at others, making it difficult to catch in repeated observations. Such an object, if confirmed, would be the closest exoplanet orbiting a Sun-like star. Even though a gas giant cannot support life on its swirling gaseous surface, it could host moons with solid ground. A large moon orbiting within the habitable zone would receive both starlight and reflected light from its planet, potentially creating stable, temperate conditions. The idea of habitable moons adds richness to the possibilities around Alpha Centauri. Though entirely speculative at present, it fuels the imagination to think of a moonlit world so close to home. The possibility of a planet or moon in the Alpha Centauri system carries profound significance. It would represent the nearest alien world to Earth, a place we could plausibly explore with future probes. Even a gas giant in the habitable zone challenges our models of planet formation and evolution in binary systems. To confirm or refute its existence is now a priority for astronomers using the most sensitive instruments available. Because the detection of S1 occurred in one observation and not in others, astronomers caution that it might be a statistical fluctuation or a noise artifact. Instrumental effects, cosmic rays, and scattered light can mimic faint sources. Confirming the object requires additional observations over time to see if it reappears in a consistent pattern. Science advances cautiously, acknowledging uncertainty and resisting the lure of wishful thinking. To solve the mystery, future telescopes with higher contrast imaging capabilities will survey Alpha Centauri. The upcoming Nancy Grace Roman Space Telescope will test advanced coronagraphs and may have the sensitivity needed to detect a planet around the bright star. Ground-based facilities using adaptive optics and longer baselines will also join the effort. Each new attempt brings us closer to an answer and demonstrates the synergy between different observatories. The challenge of detecting planets around bright, nearby stars like Alpha Centauri drives innovation. It requires suppressing starlight without blocking the faint light from any planets. Engineers design optics that cancel waves of light through interference, while others propose star shades, large screens flown thousands of kilometers from a telescope to cast a shadow on the star. These creative approaches highlight the determination to peer into our neighbors' systems. For many people, the possibility of a planet just 4 light-years away feels both tantalizing and grounding. The distance is vast on human scales, yet within the cosmic neighborhood, it is a short stroll. Thinking about Alpha Centauri prompts questions about how we might one day cross interstellar space. It connects scientific investigation with the age-old urge to explore uncharted horizons. The gravitational interplay within the triple star system is complex. Alpha Centauri A and B orbit each other every 80 years, while Proxima circles much farther out in a 500,000-year path. Any planets around A or B must orbit close enough to their host to remain stable, while those around Proxima feel the distant tug of the larger stars. Modeling these dynamics helps scientists identify regions where planets could survive for billions of years. We already know that Proxima Centauri, the red dwarf companion, hosts a planet designated Proxima b. That world, located a mere 4.2 light-years away, is the nearest known planet beyond our solar system. Its discovery raised hopes that the Alpha Centauri system as a whole might be rich in worlds. The search around the brighter pair now seeks to see whether those hopes are justified. Alpha Centauri. A and B are similar in mass and color to our Sun, making them intriguing analogues. If Earth-like planets orbit them, those planets might enjoy stable, long-lived stellar output. The idea that a twin of our Sun could have a twin of our Earth so nearby captures the imagination. Researchers continue to refine their observations, hoping to glimpse such a world. For decades, Alpha Centauri has played a role in science fiction as a future destination. Stories of colonists, explorers, and alien civilizations often choose this system because of its proximity. Reality is catching up with fiction as our instruments become capable of detecting actual worlds there. The dialogue between imagination and observation continues, each inspiring the other. Long before imaging tools improved, astronomers used radial velocity measurements to look for the tiny wobble caused by planets tugging on Alpha Centauri's stars. The signals were small and often confounded by stellar activity. Over years of data, researchers reported tentative signals and then retracted them, illustrating the difficulty of the task. These efforts laid the groundwork for more sensitive techniques. Every attempt to find a planet around Alpha Centauri teaches us more about our instruments and the stars themselves. We learn how to calibrate detectors, model stellar surfaces, and distinguish between planetary signals and star spots. Each false alarm refines our methods, bringing us closer to a definitive detection or ruling out certain types of planets. The process is iterative and rigorous, and progress comes in small steps. The story of Alpha Centauri remains open. We stand at a moment when new data might reveal a world next door, or might show that our nearest sun-like stars have no large companions. Either outcome will teach us something about planetary systems. As we continue to listen and look, our attention also turns to the broader variety of worlds that have already been found, each with its own strange beauty. The diversity of exoplanets stretches our sense of what is possible. There are super-Earths, larger and more massive than our planet, which may have thick atmospheres and deep oceans. There are mini-Neptunes, smaller versions of gas giants with hazy envelopes, and lava worlds where molten rock flows across the surface. Each category hints at complex formation histories and varied climates. Some worlds orbit their stars so closely that they complete a year in less than a day. These ultra-short period planets are scorched by relentless radiation and tidal forces. Their atmospheres may be stripped away, leaving bare, iron-rich surfaces glowing red from heat. Such extreme conditions may create rivers of metal and mineral vapor, painting landscapes we struggle to imagine. Other planets have been cast adrift into the darkness between stars. These rogue worlds, untethered to any sun, wander through the galaxy, warmed only by the faint heat left over from their formation or by internal processes. They might harbour subsurface oceans kept liquid by radioactive decay or tidal interactions if they carry their own moons. Though invisible to traditional planet-finding techniques, they represent a significant component of the galactic population. Planets have also been found orbiting binary stars, weaving their way around two suns in paths that are both stable and beautiful. These circumbinary planets experience dual sunrises and sunsets, and their climates may be more complex than those on single-star worlds. In some systems, planets orbit one star while feeling the periodic tug of the companion, creating intricate gravitational dances. Such systems challenge our intuition and enrich our understanding of planetary dynamics. Some giants are so tenuous that their bulk density is less than a lump of styrofoam. These cotton candy planets puff up under the heat of their stars, their atmospheres bloated by stellar radiation. They possess thick, extended envelopes that blur the line between planet and cloud. Their existence invites questions about how they formed and how long they can survive before losing mass to space. At the other extreme are worlds with densities greater than iron. These planets may be the stripped cores of larger bodies, whose outer layers were removed by stellar winds or collisions. Their surfaces could be covered in metallic plains and jagged mountains of alloy. They are evidence of violent processes that sculpt planetary systems. Some exoplanets may be rich in carbon, leading to speculation that their interiors contain diamond layers, or that their skies may host clouds of silica and alumina that sparkle like gemstones. While such descriptions are currently theoretical, they demonstrate how chemical composition can lead to exotic geologies. The more we learn about exoplanet atmospheres, the more surprises we are likely to encounter. Remarkably, the first exoplanets ever detected were found orbiting a pulsar, the remnant of a dead star. These planets survived or reformed after a supernova explosion, orbiting a stellar corpse that emits beams of radiation like a cosmic lighthouse. Such environments are bathed in intense particle streams, yet planets persist there. The discovery highlights the tenacity of planetary systems and points to the unexpected corners where worlds can exist. One of the most intriguing nearby worlds is Proxima Centauri b, orbiting our closest stellar neighbour. With a minimum mass around 1.3 times that of Earth, and a year lasting about 11.2 days, it sits within Proxima's habitable zone, receiving roughly 70% of the energy that our planet gets from the Sun. Its discovery demonstrated that potentially temperate, rocky planets can exist around dim red dwarfs. The finding captured headlines around the world because of its proximity and similarity to Earth in size. Proxima b lies just 4.2 light-years away, making it the closest exoplanet to us. It scores high on the Earth Similarity Index, a measure that compares a planet's size, density, and temperature to those of Earth. Though we cannot yet see its surface, the numbers alone inspire hope that it might share more than just orbital statistics with our home. The closeness of Proxima b turns it into a natural focal point for discussions of life beyond Earth. However, Proxima Centauri is a flare-active red dwarf, emitting bursts of ultraviolet and X-ray radiation that could strip away a planet's atmosphere. Proxima b is likely tidally locked, keeping one side always facing its star and the other in perpetual darkness. The day side may suffer from intense irradiation, while the night side could be frigid. For life to survive, the planet would need a resilient atmosphere or ocean to distribute heat and shield against stellar storms. Astrobiologists speculate that a thick atmosphere, rich in greenhouse gases, or a deep global ocean might create a temperate twilight zone between the hot day side and cold night side. Winds and currents could move heat around the planet, keeping the terminator region warm enough for liquid water. This scenario remains hypothetical, but it shows how life might adapt to circumstances far from Earth's familiar cycles. Proxima b challenges us to consider climate regimes beyond our experience. Surveys suggest that about 24% of red dwarfs have Earth-sized planets in their habitable zones. If this is correct, such planets may be spaced roughly 8 light-years apart, on average. The probability of finding one around the very nearest red dwarf is less than 10%, yet Proxima b exists, hinting that temperate planets around small stars could be more common than previously thought. This result reshapes our expectations about the frequency of potentially habitable worlds. The environment around a red dwarf challenges any emerging life to cope with high-energy flares and long periods of dormancy. On Earth, some organisms go dormant during droughts or radiation exposure, only to revive when conditions improve. Perhaps life on a planet like Proxima b would adopt similar strategies, hunkering down during flares and thriving during calm periods. These speculative ideas show how exoplanet diversity feeds our imagination about biological resilience. No exomoon has yet been confirmed, but hints suggest that large satellites may orbit some gas giants. A habitable moon around a giant planet could be a stable, temperate environment, even if the planet itself is inhospitable. In the Alpha Centauri system, a giant world might host moons where conditions resemble those of Earth. Detecting such moons will require precision beyond current capabilities, but the search has begun. In some systems, large gas giants act as shepherds, influencing the formation of smaller worlds through their gravity. They can protect inner planets by deflecting comets, or they might destabilize orbits, sending bodies into the star or out of the system. The arrangement of planets within a system therefore shapes the prospects for habitability on individual worlds. Each planetary family is a unique narrative of chance and interaction. To compare distant worlds, scientists use metrics like the Earth Similarity Index, which considers factors such as radius, density, and temperature relative to Earth. A high score does not guarantee habitability, but offers a way to prioritize targets for future study. Proxima B's relatively high index makes it a prime candidate, but we must also look at planets with different compositions or radiation environments. A comprehensive approach broadens our understanding of life's potential homes. As we study planets with exotic conditions, we must remember that life elsewhere may not mirror life on Earth. Organisms might use different biochemistries, rely on solvents other than water, or thrive in environments we find hostile. The molecules of life could be built from different elements, perhaps silicon-based structures or ammonia-based metabolisms. Keeping an open mind is crucial when interpreting signals from faraway worlds. Each new planet we uncover broadens our sense of the universe's richness. We see Earth not as a singular oasis, but as part of a vast family of worlds, each with its own history and potential. The realization that our planet is one among many instills both humility and connection. It encourages us to cherish our world even as we dream of others. Although the distances involved are immense, preventing direct exploration for now, the information we gather from starlight allows us to build detailed models of distant worlds. We may not walk on their surfaces in our lifetimes, but we can infer their climates, compositions, and perhaps even signs of life from afar. As we continue to push these limits, attention turns to future instruments designed specifically to find the next Earth. The dream of Earth 2.0 begins to take shape. Upcoming missions are being designed to detect and characterize Earth-like planets. The Nancy Grace Roman Space Telescope will employ a coronagraph to block starlight and gravitational microlensing to find planets by observing how their gravity bends the light of background stars. These techniques will allow detection of planets much farther from their stars and of smaller size than current surveys can probe. Roman's success will pave the way for even more ambitious observatories. One of the greatest challenges is blocking the overwhelming light of a star to see the faint reflection from a planet. The Sun is about 10 billion times brighter than Earth, and this ratio illustrates the contrast issue faced by instrument designers. Coronagraphs use masks and carefully shaped optics to cancel out starlight while preserving the planet's light. The Roman mission will test such a system in space, representing a major step toward direct imaging of Earth-sized worlds. In addition to its coronagraph, Roman will make use of gravitational microlensing, where a star and its planets act as a lens that magnifies the light of a more distant background star. The alignment produces a temporary brightening, revealing planets that would otherwise remain invisible. This method is sensitive to planets far from their stars and can detect analogues of Jupiter and even free-floating planets. Through these complementary approaches, Roman will expand the census of planetary systems. Looking further ahead, NASA is planning the Habitable Worlds Observatory, a mission dedicated to finding Earth-sized planets around Sun-like stars and studying their atmospheres for signs of life. This telescope will combine a powerful mirror with a state-of-the-art coronagraph and perhaps a starshade to achieve the necessary contrast. Its objective is not only to detect planets, but also to analyze their light to identify gases like oxygen, methane, and water vapor. Such measurements could reveal whether a planet's atmosphere has been altered by biological processes. Capturing the faint light of an Earth-like planet requires exquisite stability and precision. Any tiny movement or imperfection in the optical system can scatter starlight back into the field of view, drowning out the planet's signal. Engineers design telescopes that minimize vibrations and temperature fluctuations, employing advanced materials and intricate control systems. The challenge is akin to spotting a firefly next to a searchlight from thousands of kilometers away. Once we can isolate a planet's light, spectroscopy becomes the key to understanding its atmosphere. By spreading the light into a spectrum, scientists can identify the fingerprints of different molecules. The presence of oxygen paired with methane, for example, might hint at biological activity, because these gases react with each other and would not coexist in large amounts without replenishment. Other combinations, like water vapor and carbon dioxide, could indicate a climate capable of supporting oceans. Such biomarkers will be the focus of future observations. In the far future, even more ambitious missions may produce images showing continents, oceans, and clouds on distant planets. By mapping how light and heat vary across a planet's surface as it rotates, scientists can infer the presence of landmasses and weather patterns. Time-resolved spectroscopy could reveal seasonal changes, such as shifts in vegetation or ice cover. Although these goals remain decades away, they illustrate the trajectory of our aspirations. Gravitational microlensing surveys will play a crucial role in broadening our understanding of planetary demographics. Unlike the transit method, microlensing can detect planets that orbit far from their host stars, or even planets that have been ejected into interstellar space. By monitoring millions of stars toward the center of our galaxy, Roman and other surveys will capture rare alignments that briefly reveal hidden planets. These events are unpredictable and fleeting, requiring continuous vigilance. The search for Earth 2.0 will not be confined to space-based observatories. Ground-based telescopes, equipped with adaptive optics and interferometry, will complement space missions by providing higher resolution and larger collecting area. By combining data from multiple platforms, astronomers can cross-validate discoveries, refine orbital parameters, and study planetary atmospheres in greater detail. International collaborations will be essential to maximize the scientific return. One intriguing proposal is to use a starshade, a large flower-shaped screen launched far from the telescope that aligns perfectly to block a star's light. This configuration can achieve higher contrast than an internal coronagraph and is adaptable to different targets. Deploying and positioning a starshade requires precise formation, flying over tens of thousands of kilometers. Though technically challenging, the concept offers a promising path to imaging Earth-like planets around nearby stars. Future telescopes may also detect exomoons by observing subtle variations in a planet's transit, or by directly imaging large satellites. Moons could contribute to habitability by stabilizing a planet's rotation, or by providing additional environments for life. Discovering such moons would add another dimension to our understanding of planetary systems. Their detection will likely follow the successful imaging of planets themselves. The progression from detecting exoplanets to characterizing them marks a shift in focus. Early surveys asked whether planets exist. Now we ask what they are like. Measuring atmospheric composition, pressure, and temperature will help determine whether a planet could sustain life. We may even be able to detect surface processes, such as volcanism or the presence of oceans, by analyzing variations in emitted and reflected light. The term Earth 2.0 conjures an image of a distant twin, a world with blue oceans, green continents, and perhaps its own web of life. Finding such a planet would be a transformative moment in human history, altering our understanding of our place in the universe. The search is not only scientific, but also deeply philosophical, appealing to our desire for connection. Knowing that another Earth-like world exists would change how we view our own planet. Interpreting signs of life will be challenging. Abiotic processes can produce gases like oxygen or methane, and the presence of water vapor does not guarantee habitability. We must consider the context of the planet, its star, and its geochemical cycles. Multiple lines of evidence will be needed before we can confidently claim to have detected life. Skepticism and rigorous analysis will remain essential, even amid excitement. In parallel with remote observations, some visionaries propose sending tiny interstellar probes propelled by powerful lasers to nearby stars. Projects like Breakthrough Starshot imagine wafer-sized spacecraft traveling at a significant fraction of light speed, reaching Alpha Centauri in a few decades. Such missions could, in principle, send back close-up images and data from planets around our nearest neighbor. The technological hurdles are enormous, but the concept captures the spirit of exploration. Our fascination with other worlds naturally leads to thoughts of whether any harbor intelligent life. Should we detect signatures that cannot be explained by natural processes, such as unusual heat patterns, organized radio emissions, or atmospheric compositions suggestive of industrial activity, we would be confronted with the profound question of whether we share the galaxy with other civilizations. While speculative, these possibilities influence the design of future instruments and inspire the dreams of many. Every mission, whether it discovers a new planet or refines an observation, pushes the boundary of what we can know. Engineers and scientists collaborate across disciplines, combining physics, chemistry, computer science, and mathematics to solve complex problems. The drive to understand our cosmic neighborhood unites diverse talents and fosters technological advances that benefit other fields. The history of astronomy is a testament to human ingenuity and curiosity. Compared to the age of the universe, our exploration of exoplanets has lasted but an instant. We are still at the beginning, with many questions unanswered and many tools yet to be built. Patience and persistence are necessary virtues, as progress often comes slowly and unpredictably. The timescale of discovery spans generations, linking present researchers with future ones who will inherit and extend the quest. As we contemplate distant worlds, we also reflect on ourselves. The act of searching for other Earths leads us to appreciate the fragility and uniqueness of our own. It underscores our responsibility to care for the only home we currently possess, even as we look outward. The journey is both outward and inward, intertwining science with philosophy. We end this segment not with answers, but with an open horizon. The possibilities raised by exoplanets, habitable zones, and nearby systems set the stage for deeper discussions about life and civilization in the cosmos. Each discovery is a stepping stone, guiding us toward questions that will be explored in the parts to come. The story continues to unfold, inviting us to listen closely to the whispers of distant worlds. As our journey continues, the glow of distant stars fades into a background hum, and we step into a landscape shaped not by mountains or planets, but by ideas. We have wandered through ancient myths and speculative visions, and now we cross a threshold into the realm of equations and paradoxes. This phase of the voyage is quieter, more contemplative, inviting us to consider the odds of companionship in a universe that seems both endless and silent. The whispers of mathematicians and astronomers mingle with the rustle of cosmic winds, and the night sky becomes a canvas for calculations that stretch our imagination. The quest to quantify the possibility of other minds began with a simple but profound question. How many communicative civilizations might exist in our galaxy? To answer that, astronomer Frank Drake proposed a chain of factors, each one representing a stage in the long journey from stardust to radio waves. In his formulation, the rate of star formation sets the stage for planets to form, and then the number of planets in habitable zones determines where life might arise. Each subsequent term considers the fraction of planets where life actually begins, evolves into intelligence, develops technology that could be detected across interstellar distances, and finally, how long such civilizations remain communicative. For decades, many of these factors were educated guesses at best. Scientists could estimate the number of stars forming each year in the Milky Way, but the fraction of stars with planets and the number of Earth-like worlds in those systems remained elusive. The search for exoplanets changed that. With instruments like the Kepler Space Telescope and other dedicated surveys, we have confirmed thousands of planets around other stars. The data suggest that a significant portion of stars, perhaps as many as 1 in 5, have planets in their habitable zones where liquid water could exist. This realization has transformed the first few terms of the equation from speculation into measurable quantities. As researchers refine the numbers, they have proposed new ways to interpret the equation. Instead of predicting how many civilizations are broadcasting right now, some ask whether any other technological species have ever arisen in cosmic history. This perspective removes the term that describes the longevity of civilizations and focuses on whether advanced life has occurred at least once beyond Earth. When scientists multiply the number of habitable planets by the probability of life developing and then of intelligence and technology emerging, they derive a threshold. If the chance of technological life appearing on a habitable planet is greater than 1 in 10 billion trillion, then statistically, other civilizations almost certainly existed at some point in the galaxy's past. This is known as the pessimism line. Only when the odds are lower than this does humanity stand alone. Imagining such infinitesimal probabilities can be dizzying. A 1 in 10 billion trillion chance is a needle in a haystack, multiplied by another haystack, and then again, many times over. Yet the size of the universe provides innumerable haystacks. Our galaxy alone contains hundreds of billions of stars, each potentially orbited by planets. If just a tiny fraction of those planets are habitable, and the emergence of technology is only slightly less improbable than the pessimism line, the cosmic ledger hints that we are not unique. The equation thus plays a dual role. It fosters humility by reminding us of the vastness of possibility, and it inspires curiosity about how rare or common our path may be. The Drake equation also underscores the interplay between astronomical discovery and biological mystery. We have filled in many of the cosmic terms through observations, but the biological terms remain uncertain. How often does life begin when conditions permit? Once it begins, how frequently does it evolve into complex organisms capable of thought and communication? These questions connect astrophysics with chemistry, geology, and evolutionary biology. They are not easily answered by telescopes alone. Laboratory studies of abiogenesis, the early evolution of life on Earth, and the search for biosignatures in exoplanet atmospheres may eventually provide clues, but for now, they remain variables with wide error bars. Our growing catalogue of exoplanets also invites us to refine our expectations about habitability. The traditional concept of a habitable zone is a range of distances from a star where a planet with a suitable atmosphere could maintain liquid water. But habitability is influenced by more than distance. Planetary size, atmospheric composition, geological activity, and magnetic fields all play roles in maintaining stable, life-friendly environments. Tidally locked planets around red dwarf stars may experience extreme temperature differences between their day and night sides. Super-Earths may have thick atmospheres or high gravity that affect surface conditions. As we learn more, the term NE in the equation, the number of habitable planets per star, becomes a spectrum rather than a single number. The revised versions of the Drake equation also consider that advanced civilizations might not be transmitting radio signals intentionally. We might detect them by identifying industrial pollutants or greenhouse gases in their atmospheres, or by observing megastructures like Dyson swarms that harvest starlight. These possibilities widen the scope of what qualifies as a detectable civilization. They also remind us that the equation is not a fixed law, but a framework for organizing our ignorance. Each new discovery adds nuance to the factors and may reveal additional terms we had not considered. Standing in the shadow of this equation, it is easy to feel both empowered and overwhelmed. On one hand, we have numbers that tether our dreams to the fabric of reality. On the other, the uncertainties in those numbers are so large that we can only grasp broad orders of magnitude. Yet the process of refining these estimates is itself a testament to human curiosity. Each exoplanet detection, each modelling of atmospheric chemistry, and each examination of early Earth conditions brings us closer to understanding our cosmic context. The Drake equation serves as a compass, guiding our explorations and inviting us to imagine what other minds might be contemplating under alien skies. While equations give us tools to estimate, paradoxes challenge us to confront the mismatch between expectation and observation. One such paradox has haunted the minds of scientists and philosophers alike. If the universe is filled with countless stars and has existed for billions of years, why do we see no clear evidence of other advanced civilizations? This conundrum is often encapsulated in a simple question asked by physicist Enrico Fermi during a lunchtime conversation. Where is everybody? The question is deceptively straightforward, but its implications reach deep into our understanding of time, space, and evolution. The paradox arises because even with conservative estimates, there seems to have been ample time for technological civilizations to arise, develop interstellar travel, and spread across the galaxy. Given the age of the Milky Way and the speed at which a motivated civilization could theoretically send probes or ships to nearby stars, the galaxy could be traversed in a fraction of its current age. If we expect multiple civilizations to exist or have existed, we might also expect at least some of them to leave signatures, signals, artifacts, or even evidence of large-scale engineering. Yet as we scan the skies with sensitive instruments, we find no undeniable signs of their presence. One reason the paradox endures is that our expectations are shaped by human experience. We are a species that has explored every continent, devised technologies to communicate across the globe, and looked up at the stars with a desire to reach them. It is natural to project this trajectory onto hypothetical extraterrestrial cultures. But the assumption that other civilizations would expand like ours is a conjecture, not a certainty. Some worlds might develop technologies, but remain content within their own systems. Others might prioritize introspection or adopt philosophies that discourage outward expansion. Our perspective is but one of many possible paths. Still, the silence invites speculation. Some researchers suggest that we may not have looked in the right way. Early SETI efforts focused on narrowband radio signals, but we now recognize that alien technologies might use different wavelengths or communication methods altogether. Others propose that advanced societies could employ communication systems based on quantum entanglement or gravitational waves, technologies beyond our current capabilities to detect. In this view, the silence may reflect our technological infancy rather than an absence of neighbors. The Fermi paradox also highlights the incomplete state of our knowledge. We have begun to fill some terms of the Drake equation through exoplanet discoveries, but other terms remain blank. We do not know the fraction of planets where life arises, the fraction where intelligence evolves, or the fraction where technology becomes detectable. Until these values are constrained, our expectations remain tentative. The paradox thus serves as an invitation to deepen our scientific inquiries and to remain humble about our assumptions. Another aspect to consider is timing. Civilizations could arise and vanish over cosmic intervals, leaving only subtle traces. If technological societies are rare and short-lived, then the overlap between any two may be small. The galaxy is vast, and signals weaken with distance. An advanced civilization might have broadcast a beacon millions of years ago, but by the time the signal reaches us, it may be faint or lost amid cosmic noise. Similarly, we may be too early or too late to detect the activities of others. The silence may thus result from the asynchronous nature of cosmic history, rather than a complete absence of neighbors. When we contemplate the Fermi paradox, we also confront a philosophical mirror. The question, "Where is everybody?" is intertwined with deeper inquiries about our own destiny. Are we capable of surviving long enough to explore the stars? Will we choose to broadcast our existence loudly, or will we retreat into quiet introspection? The paradox is not merely about aliens. It is about the trajectories that intelligent life might take when faced with the vastness of space and the challenges of sustainability. One line of thought that addresses the silence is the concept of a great filter. This hypothesis proposes that somewhere along the path from simple chemistry to spacefaring technology lies a step that is extremely improbable. The filter could occur early, perhaps at the origin of life itself. Conditions conducive to life may be common, but the actual emergence of self-replicating molecules might be vanishingly rare. If so, then the universe could be teeming with habitable planets that nevertheless remain sterile. Alternatively, the filter might lie in the progression from single-celled life to complex multicellular organisms. On Earth, simple life appeared relatively quickly after the planet cooled, but it remained microscopic for billions of years. The transition to eukaryotic cells, sexual reproduction, and complex body plans may be so improbable that few planets achieve it. In this scenario, microbial life might be widespread, yet complex life, and by extension, intelligence, would be exceedingly rare. We may share the cosmos with countless microbes, but few peers with whom to converse. The filter might also reside much later, after civilizations have developed advanced technology. Technological societies could face obstacles such as resource depletion, environmental degradation, runaway artificial intelligence, or catastrophic wars. These hurdles might be difficult to overcome, leading to self-destruction before interstellar exploration becomes feasible. If the filter is in our future, it serves as a warning. Our survival may depend on recognizing and navigating these risks with wisdom and foresight. Related to the Great Filter is the rare Earth hypothesis, which argues that while microbial life may be common, complex life requires a confluence of fortunate conditions. Our planet benefits from a stable orbit around a long-lived star with relatively low ultraviolet radiation. Its distance from the Sun allows liquid water while avoiding tidal locking. The presence of a large moon stabilizes Earth's axial tilt, moderating seasonal extremes. Gas giants like Jupiter shield the inner solar system from excessive cometary bombardment. Earth's magnetic field, generated by a molten core, protects the atmosphere from solar wind. Plate tectonics recycle nutrients and regulate the climate, and the timely rise of atmospheric oxygen allowed the development of complex multicellular organisms. Each of these factors may be rare in combination, rendering Earth a precious oasis. Some scientists question whether all these conditions are strictly necessary. For instance, gas giants might not always be required to shield inner planets, and multiple pathways to complexity may exist. Nonetheless, the rare Earth hypothesis underscores the fragility of the circumstances that support us. It suggests that even if habitable zones and basic life are common, the road to intelligence could be narrow and winding. In this view, our existence is not guaranteed by the laws of physics alone. It is the result of a remarkable sequence of coincidences. The Great Filter concept intertwines with existential risk. If the filter lies in our future, then the same factors that could silence other civilizations may threaten our own. Nuclear warfare, uncontrolled climate change, runaway artificial intelligence, engineered pathogens, and other hazards could curtail our progress or extinguish our species. These threats are not purely speculative. They are woven into the fabric of contemporary society. Recognizing them prompts us to act responsibly, to steward our planet, and to develop technologies with caution. If we hope to join the ranks of long-lived civilizations, we must navigate the filter deliberately. Thinking about the filter as a future hurdle can be unsettling, but it also offers a call to action. It encourages us to examine the pathways that lead to self-destruction and to search for ways to avoid them. It reminds us that intelligence alone does not guarantee survival. Wisdom and adaptability are equally important. In a sense, the silence of the cosmos becomes a cautionary tale. We cannot assume that progress will inevitably lead to a bright future. We must cultivate resilience, empathy, and foresight to ensure that we are not halted by the same forces that may have stilled others. While some solutions to the Fermi paradox emphasize existential threats, others suggest that the patterns of growth and expansion we take for granted may not be sustainable on cosmic scales. The sustainability solution proposes that civilizations rarely embark on unchecked exponential expansion, because such growth exhausts resources and leads to collapse. In this view, the absence of obvious galactic empires is not evidence of absence, but rather a sign that advanced societies either limit their growth or succumb to the consequences of overconsumption. Historical examples on Earth support the idea that rapid expansion often ends in decline. The mysterious collapse of the population on Easter Island illustrates how resource depletion can undermine a society. When the islanders overused their forests to build canoes and monuments, the loss of trees led to soil erosion, decreased food production, and social upheaval. Conversely, there are human cultures that have maintained low population densities and sustainable practices over millennia, such as some hunter-gatherer groups. These examples suggest that long-term survival may favor steady or slow growth, rather than explosive expansion. Applying this logic to extraterrestrial civilizations implies that if other species exist, many may follow sustainable development patterns that leave little detectable footprint beyond their home systems. Their energy use and population size might remain within ecological limits. They may harness their local star, recycle resources meticulously, and avoid large-scale colonization. Such societies would be difficult to detect across interstellar distances, not because they are not there, but because they live within their means. The sustainability solution also allows for civilizations that expand and then collapse. A society might attempt to colonize nearby systems, experiencing a burst of growth as it spreads through the galaxy. Yet the challenges of maintaining interstellar infrastructure, the time delays in communication, and the energy demands of travel could strain its capacity. Over generations, the civilization might splinter into isolated pockets, decline or transform into something unrecognizable. The remnants could be quiet or technologically diminished, leaving no obvious megastructures or continuous signals. In our own time, we see hints of how growth patterns could shift. After centuries of increasing population, global human growth is slowing. Fertility rates in many countries have fallen, and projections suggest that the world population may peak later this century and then stabilize or decline. This deceleration results from factors such as urbanization, education, and access to healthcare. It exemplifies how societies adapt to finite resources and changing values. If our species chooses a sustainable trajectory, we may focus on enhancing quality of life rather than expanding outward at any cost. Exploring sustainability on a galactic scale also reframes our expectations of contact. We often imagine encountering fleets of interstellar ships or hearing powerful beacons. Instead, we might discover subtle signs: a faint anomaly in a planet's atmosphere, a slight excess of infrared radiation from waste heat, or an unusual arrangement of orbiting structures. These clues would require careful observation and interpretation. They would also demand that we remain patient and open-minded. The absence of fireworks does not equate to emptiness. Sometimes, what is quiet is simply living within its limits. The interplay between sustainability and the great filter reminds us that survival is a balancing act. Civilizations that ignore ecological realities may burn brightly and briefly, whereas those that heed limits may endure but remain inconspicuous. Whether we choose to send signals or to listen quietly, our fate will hinge on our ability to harmonize our aspirations with the constraints of our environment. The sustainability solution challenges the narrative of inevitable expansion and invites us to imagine long-lived cultures that thrive by doing less. As we contemplate the possibility of slow or collapsed civilizations, we also reflect on our own stage of development. Our species has begun to explore beyond Earth, sending probes to other planets and telescopes into space. We have also experienced the consequences of unsustainable practices: deforestation, pollution, biodiversity loss, and climate change. These experiences teach us that our current trajectory is not guaranteed to lead to a stable, advanced future. If we hope to detect others, and to be detected in turn, we must consider how our choices shape our visibility and longevity. Beyond equations, paradoxes, and filters lies the emotional dimension of the search. The great silence of the cosmos can feel eerie or profound, depending on our perspective. It could signify that we are alone, a solitary spark in a vast darkness. It could mean that life is rare, or that others are too far away, or too quiet for us to notice. It might also mean that the universe is filled with life that chooses a different path. communicating in ways we have yet to imagine, or remaining deliberately silent to protect themselves. The idea that civilizations might hide is sometimes called the zoo hypothesis or the dark forest scenario. In one version, advanced societies observe emerging civilizations like ours, but avoid contact to allow natural development or to prevent cultural contamination. In another, civilizations remain silent out of fear. They assume that any signal could invite predatory attention, so they adopt a policy of radio quietness. These scenarios explore the social dynamics of intelligence on a cosmic scale. They remind us that our search is influenced not only by physics and biology, but also by psychology and sociology. The Great Silence also prompts introspection about our own desires and fears. Why do we seek others? Is it to alleviate loneliness, to learn from different perspectives, or to affirm that we are not an anomaly? Do we fear contact because of potential threats, or do we long for it as a source of inspiration? The answers to these questions shape the stories we tell and the research we pursue. They reveal that the search for extraterrestrial intelligence is as much about understanding ourselves as it is about finding others. There is a humility in recognizing that we occupy a tiny corner of an immense universe. The stars we see at night are but a fraction of those in our galaxy, and our galaxy is one among trillions. The cosmic distances involved are so vast that even light, our fastest messenger, takes years to traverse the gap between stars. This vastness means that even if intelligent life is common, the separation between civilizations could be measured in thousands or millions of light years. Messages exchanged across such expanses would feel like whispers across epochs, requiring patience and perseverance to interpret. At the same time, the silence has fostered a sense of agency. Knowing that our planet is currently the only known harbour of life imbues us with responsibility. We are the stewards of an entire biosphere, a mosaic of species and ecosystems that arose through eons of evolution. Our actions can protect or imperil this delicate balance. In pondering the absence of contact, we are reminded that our first duty is to our own world. The search for others should not distract from the care of home. Rather, it should illuminate the preciousness of what we have. Preparing to explore the possibility of ancient civilizations closer to home requires us to approach the silence with fresh eyes. If galaxies have hosted technological species long ago, their traces may not lie in distant stars, but in our own neighborhood. Remnants of probes, artifacts, or subtle modifications to planetary environments could reside within the solar system. The search for such evidence requires careful examination of asteroids, moons, planets, and comets. It also demands that we question assumptions about what constitutes an artifact and how time erodes or preserves technology. In our next steps, we will shift our gaze inward to the planets and moons that share our star. We will consider the possibility that the cosmic neighbours we seek may have been here before us, leaving behind whispering traces for us to uncover. The story of ancient civilizations within our solar system invites us to blend imagination with scientific inquiry. It calls us to look at familiar worlds with a renewed sense of wonder and to consider that the great silence may hide secrets just beyond our doorstep. But before we turn to those nearby realms, let us linger for a moment in this balance of equations and paradoxes. The Drake equation offers a framework for hope, hinting that we may not be unique if the probabilities align. The Fermi paradox tempers that hope with a challenging question, urging us to look beyond our assumptions. The great filter reminds us of the fragile steps that lead from chemistry to consciousness. And the rare Earth hypothesis humbles us with its list of necessary conditions. The sustainability solution invites us to reimagine growth and to find harmony with our environment. As the night deepens and the stars wheel overhead, these ideas coalesce into a tapestry of curiosity and caution. The universe may be silent because life is scarce, because civilizations are fleeting, or because they choose to remain quiet. It may be vibrant with voices we cannot yet hear. Whatever the truth, our willingness to ask and to explore speaks to the essence of our species. We are question askers and story weavers, drawn toward the unknown. In the next chapter of our journey, we will carry this inquisitive spirit with us, seeking clues not just among the stars, but within the stones and ice of our own cosmic backyard. To understand why the Drake equation ignites such fascination, it is helpful to explore each of its factors more deeply. The first term, often denoted R star, represents the rate at which suitable stars form in our galaxy. Not all stars are equal candidates for habitable planets. Massive stars burn quickly and emit intense radiation, while very small stars can be unstable. Sun-like stars and smaller, long-lived red dwarfs provide the longest windows for life to evolve. Astronomers use observations of star formation regions and stellar evolution models to estimate R star, arriving at a value of a few new stars per year in the Milky Way. The next term considers the fraction of those stars that host planetary systems. For much of history, this fraction was pure speculation. The detection of exoplanets has now shown that planets are common. The Kepler mission revealed that most stars likely have at least one planet, with many hosting multiple. This finding revolutionized our understanding of cosmic architecture. It means that there are potentially hundreds of billions of planets in our galaxy, each a potential laboratory for chemistry and perhaps life. Beyond simply existing, a planet must reside in a region where conditions can support liquid water on its surface. The concept of a habitable zone, sometimes called the Goldilocks zone, derives from this requirement. If a planet is too close to its star, water may evaporate. If too far, water may freeze. However, recent research suggests that habitability is more complex. Subsurface oceans, geothermal energy, and atmospheres rich in greenhouse gases could allow life to exist outside traditional habitable zones. Moons around gas giants and rogue planets drifting between stars might host internal oceans beneath layers of ice, warmed by tidal forces or radioactive decay. Estimating the fraction of planets that develop life, often represented as FL, is one of the most challenging steps. On Earth, life appeared relatively early in the planet's history, emerging within a few 100 million years after the crust cooled. Some scientists interpret this rapid appearance as evidence that life arises readily when conditions permit. Others caution that one data point is insufficient to draw conclusions. Life may require a rare combination of chemical ingredients, energy sources, and stability that seldom coincide, making Earth's story atypical. To progress from simple life to intelligent beings capable of technology involves additional steps. The development of complex multicellular organisms on Earth was delayed for billions of years. Single-celled organisms dominated for most of the planet's history. The emergence of eukaryotic cells with internal structures, the invention of sex, the rise of oxygen in the atmosphere, and the Cambrian explosion of diverse body plans were critical milestones. Each of these transitions may be unlikely, and each could represent a filter through which many worlds never pass. Intelligence itself is multifaceted. Many animals display problem-solving abilities, social structures, and communication. However, only a few have produced technologies that could be detected from space. The fraction f sub I, representing planets where intelligence emerges, and f sub c, representing those where communicative technology develops, reflect complex interactions between biology, environment, and culture. Our species stands as a single example. We cannot yet know whether intelligence is an inevitable outcome of evolution or a rare fluke. The term L in the original equation measures the duration of a civilization's detectable phase. A society may discover radio, but then move on to different communication methods, or lose the capacity to transmit at all. Civilizations might undergo cycles of technological bloom and decline. By reformulating the equation to consider whether any technological civilization has ever existed, researchers circumvent the need to specify L. This shift in perspective emphasizes the cumulative history of the cosmos, rather than the present moment alone. The sheer scale of the numbers involved in these calculations can obscure their emotional impact. When we talk about 1 in 10 billion trillion, we refer to a probability so small that it is almost beyond comprehension. Yet multiplied by the vast number of planets, even such minuscule probabilities can yield non-zero expectations. Thinking in such scales challenges our intuition. It requires us to accept that events that seem impossible on human timescales become plausible across cosmic expanses. There is also the question of timescales. Stars and planets endure for billions of years. Civilizations, by contrast, are fleeting. Modern human technology has existed for only a few centuries. Even if intelligent life is common, the overlap between the active phases of two civilizations may be brief. A species may rise, fall, and disappear before its signals reach a distant observer. Thus, the cosmic silence may be a matter of timing rather than a definitive statement about abundance. Expanding on the Fermi paradox, some scientists have proposed that the galaxy may be filled with self-replicating probes that explore and perhaps seed life. These theoretical machines, often called von Neumann probes, could traverse interstellar space by building copies of themselves from raw materials in asteroid belts and planetary systems. If such probes were feasible, and if any civilization chose to deploy them, the galaxy could have been saturated with artifacts in relatively short cosmic timescales. The absence of evidence for these probes is therefore another facet of the paradox. It suggests either that such technologies are impossible, undesirable, or that we have not yet recognized them. Other solutions to the paradox revolve around the idea that we are early in the cosmic timeline. The heavy elements necessary for rocky planets and life were forged in previous generations of stars. It took billions of years for the universe to produce enough metals to build Earth-like worlds. Thus, complex life might only now be emerging in many galaxies. If this is the case, we may be among the first species to reach technological maturity, and the galaxy will become more populated with time. This perspective reframes the silence as a temporary lull rather than a permanent state. The possibility of a galactic catastrophe resetting civilizations is another proposed explanation. Events such as gamma-ray bursts, supernovae, or massive asteroid impacts could periodically sterilize regions of the galaxy. If such cataclysms occur frequently enough, they may prevent the accumulation of long-lived technological societies. On Earth, mass extinctions have reshaped the evolutionary trajectory multiple times. The most severe, like the Permian-Triassic event, eliminated the majority of species. A galaxy-wide version of such events could repeatedly push intelligent life back to early stages. The zoo hypothesis posits that advanced civilizations deliberately avoid contact, allowing emerging species to evolve without interference. This scenario imagines the galaxy as a protected reserve where our development is observed from afar. The reasons for such non-interference could range from ethical considerations to a desire to study natural evolution. While speculative, the zoo hypothesis underscores the role of agency and choice in cosmic interactions. It suggests that even if we are surrounded by intelligence, we might remain unaware unless those beings choose to reveal themselves. Some thinkers propose that interstellar travel may be far more difficult or energy-intensive than our science fiction imagines. Even at a fraction of light speed, traveling to the nearest stars would take decades or centuries. The energy required to accelerate a spacecraft to such speeds is enormous. Moreover, hazards like interstellar dust and radiation pose significant challenges. If the practical barriers to interstellar travel are insurmountable, then civilizations may remain isolated by necessity rather than choice. In this view, the absence of visitors is not surprising. The stars are simply too far away. It is also conceivable that technological civilizations do not prioritize exploration or communication. They may turn their energy inward, focusing on virtual realities, computational simulations, or other pursuits that do not involve physical expansion. Advanced technologies could allow minds to exist in forms that are difficult for us to detect, such as in microscopic computers powered by starlight, or in systems distributed within gas clouds. Such civilizations might be present, but invisible, their footprint blending into the natural background. The Great Filter, in its broadest sense, invites us to consider the chain of improbable events that lead to beings capable of pondering their origins. The list of potential filters begins with star formation itself, which required primordial density fluctuations in the early universe. The subsequent condensation of heavy elements from ancient supernovae seeded protoplanetary disks with the building blocks for rocky worlds, planetary formation, stable climates, the emergence of replicating molecules, and the transition to cells are each possible bottlenecks. Moving forward, the development of photosynthesis, which transformed Earth's atmosphere and allowed energy to be harvested from sunlight, was a critical innovation. The oxygenation of the atmosphere enabled the evolution of aerobic metabolism, providing more energy for complex life. The appearance of the eukaryotic cell, with its nucleus and organelles, allowed for greater specialization. Multicellularity permitted organisms to evolve tissues and organs. Nervous systems and brains enabled complex behavior. Each of these steps could be rare or require unique circumstances. Consider the evolution of tool use and culture. Many animals use objects in their environment, but the transition to sophisticated tool making is relatively rare. Primates, certain birds, and sea otters display basic tool use. Human ancestors refined this skill over millions of years, developing stone tools, harnessing fire, and eventually creating machines. Culture, shared knowledge passed down through generations, compounds innovation. It is conceivable that on most planets, intelligent life remains at a stage equivalent to the great apes or dolphins, never crossing the threshold into technological civilization. Late filters may take the form of self-inflicted disasters. The invention of nuclear weapons introduced the possibility of global destruction. Climate change, driven by greenhouse gas emissions, threatens ecosystems and societies. Artificial intelligence, if misaligned with human values, could cause unintended harm. Biotechnology could unleash engineered pathogens. Each of these risks requires deliberate management. The ability to foresee and mitigate global threats may be as crucial for survival as scientific or technological prowess. Asteroid impacts and volcanic eruptions also pose threats to civilizations. The impact that led to the extinction of the non-avian dinosaurs was a random event that reset Earth's evolutionary stage. Massive volcanic eruptions, like those forming large igneous provinces, can release vast amounts of gases and aerosols, altering climate. Over geological timescales, such events are inevitable. For a technological civilization, preparedness, through monitoring, deflection technologies, or resilient infrastructure, could determine survival. A society that fails to develop these capabilities may fall prey to natural cataclysms. The rare Earth hypothesis takes a different approach to explaining scarcity. Instead of focusing on improbable events, it emphasizes the need for specific environmental conditions. A planet's orbit must be nearly circular to avoid extreme temperature variations. It must have sufficient mass to retain an atmosphere and maintain geological activity. Its composition must include the right mix of elements to build complex molecules. Its host star should be stable, neither too hot nor too prone to flares. The planet should reside far from regions of intense radiation, like supernova remnants or active galactic nuclei. Galactic location is critical. The inner regions of a galaxy contain more metals, but also higher radiation and gravitational perturbations. The outer regions may be too poor in heavy elements to form rocky planets. A position within a galactic habitable zone ensures a balance between chemical richness and safety. Earth sits in a relatively quiet part of the Milky Way, far from the crowded center. This tranquility may have protected life from cosmic hazards. Such calm neighborhoods might be rare in spiral galaxies, and even rarer in irregular galaxies or dense clusters. The presence of a large moon influences a planet's climate stability. The moon slows Earth's rotation and stabilizes its axial tilt, leading to moderate seasons. Without this stabilizing effect, Earth's tilt could vary dramatically over geological timescales, causing extreme climate swings. These variations might hinder the long-term persistence of complex ecosystems. Additionally, the tides created by the moon may have played a role in the evolution of early life, creating nutrient-rich tidal pools and influencing cycles of wetting and drying that encourage chemical complexity. Earth's magnetic field shields the surface from charged particles in the solar wind and cosmic rays. Without this protection, the atmosphere could be stripped over time, and radiation at the surface would be higher. Mars, for example, lost much of its atmosphere, partly because its magnetic field weakened. A planet needs a molten, convecting core to generate a magnetic field. This requirement ties back to planetary size, composition, and heat production. Planets too small may cool rapidly, shutting off their magnetic dynamos. Plate tectonics play a crucial role in regulating climate. The movement of continents redistributes heat and influences ocean currents. The subduction and recycling of crustal material drive the carbon-silicate cycle, which acts as a thermostat, removing carbon dioxide from the atmosphere at high temperatures and releasing it at low temperatures. Without tectonic activity, a planet may lack this buffering system, making it vulnerable to runaway greenhouse effects or freezing episodes. The existence of tectonics depends on internal heat, water content, and crustal thickness, attributes that may be rare. The rise of atmospheric oxygen is another vital piece of the puzzle. For most of Earth's history, oxygen levels were low. It wasn't until cyanobacteria evolved photosynthesis that oxygen began to accumulate. Even then, it took hundreds of millions of years for oxygen to reach levels that support large animals. Oxygen enables efficient energy production in cells and allows for protective ozone to form, shielding life from harmful ultraviolet radiation. Planets without similar oxygenation events may be locked in microbial eras indefinitely. The rare Earth hypothesis paints a picture of finely tuned circumstances, but it is not without critics. Some argue that life and intelligence could flourish under different conditions. For example, tidal locking on planets around red dwarfs might create habitable twilight zones. Magnetic field alternatives could protect atmospheres, such as thick crusts or atmospheric flows. Photosynthesis might evolve using different pigments or energy sources. Plate tectonics may not be essential if other mechanisms regulate climate. The universe could harbor life in forms unfamiliar to us, adapting to environments we would consider extreme. Nevertheless, rare Earth considerations encourage us to appreciate the fragility of our situation. They highlight that our planet's history is a series of unlikely events and beneficial circumstances. Whether these events are truly rare or not, they inspire gratitude and caution. The more we understand about Earth's uniqueness, the more motivated we become to preserve it. Our planet's life support systems are intricate and interconnected. Destabilizing one component can reverberate through the whole. The sustainability solution, when applied to the cosmos, operates on the same principle of interconnectedness. In ecology, population growth is often modeled by logistic curves, where rapid expansion is tempered by limiting factors such as food, space, or competition. Populations that exceed their carrying capacity decline sharply. In human societies, resource scarcity, pollution, and social stress can trigger collapse. These patterns suggest that unrestrained exponential growth is not a stable long-term strategy. If civilizations on other worlds follow similar dynamics, the galaxy may favor those that adopt sustainable practices. Exponential growth in energy consumption is particularly unsustainable. As a civilization uses more energy, it must dissipate more waste heat. On a planetary scale, excess heat can alter climate. On a galactic scale, if a civilization attempted to harness the energy output of many stars, the aggregate waste heat could change local environments. This notion has led researchers to search for infrared signatures of waste heat as potential indicators of advanced technology. The lack of such detections suggests either that few civilizations reach such scales, or that they manage their energy in ways that minimize detectable waste. The example of Easter Island is often cited as a microcosm of unsustainable growth. The islanders expanded their population and erected enormous statues, consuming trees to transport and raise them. Over time, deforestation depleted the resources needed for canoes, homes, and soil fertility. The society declined dramatically. This cautionary tale illustrates how cultural and environmental factors intertwine. It also underscores that collapse can occur even in isolated systems, and that a civilization's greatest achievements may inadvertently sow the seeds of its decline. In contrast, some human groups have maintained stable populations and harmonious relationships with their environment. The Kungsan people of the Kalahari Desert, for example, live as hunter-gatherers with low population density, relying on extensive knowledge of their ecosystem. They exemplify a slow growth model that has persisted for tens of thousands of years. Such societies demonstrate that it is possible to thrive without expanding endlessly. They also highlight the diversity of human adaptations to varying environments. Global demographic trends show a shift towards slower growth. The demographic transition model describes how societies move from high birth and death rates to low birth and death rates as they industrialize and develop. Improved healthcare, reduces mortality, and education, particularly of women, along with urbanization, leads to smaller family sizes. Economic considerations and access to contraception further lower fertility. As a result, many countries now have aging populations, and global growth rates have declined significantly compared to the 20th century. Projections suggest that global population may peak at around 10 billion people within this century. After peaking, the population is expected to stabilize or even decrease. This projection challenges earlier fears of unchecked population explosion and reveals that human societies can adapt to resource constraints and changing values. However, these trends are uneven across regions. Some areas continue to experience high growth, while others face declining numbers. Understanding and managing these variations will be crucial for global stability. Energy consumption patterns also reveal important lessons. For much of history, societies relied on wood, charcoal, and simple biomass. The Industrial Revolution shifted our reliance to coal, then oil, and natural gas. Each transition increased energy availability and spurred growth. But fossil fuels are finite and emit greenhouse gases that alter the climate. The pursuit of renewable energy, solar, wind, hydro, geothermal, reflects an awareness that sustainable energy sources are essential for long-term prosperity. Advanced civilizations elsewhere may face similar transitions, balancing the convenience of fossil fuels or equivalent sources against environmental costs. Beyond planetary energy budgets lies the concept of harnessing a star's output. A civilization that encloses its star with orbiting collectors to capture most of its energy, hypothetical megastructures known as Dyson spheres, would operate on scales we can barely imagine. While such structures might be efficient for energy harvesting, their waste heat would radiate in infrared wavelengths, potentially detectable by distant observers. Searches for such excesses have not revealed definitive evidence. This absence may reflect the rarity of such endeavors, the limitations of our surveys, or alternative energy strategies employed by advanced societies. The sustainability solution does not negate the possibility of cosmic exploration. Instead, it suggests that expansion may occur at a deliberate pace. Civilizations might send probes or small colonies to nearby systems, then pause to assess impacts, develop resources, and stabilize. Expansion could be more like a creeping vine than a wildfire. Over millions of years, such slow growth could still populate large swathes of the galaxy, but it would leave fewer obvious markers at any given time. This scenario aligns with the notion that we may need to search patiently and carefully for subtle signs. Considering the prospect of collapse also invites introspection about resilience. Civilizations that collapse may not vanish entirely. They could regress to simpler states or disperse into smaller communities. In such cases, technology might be lost or repurposed, leaving little trace. On Earth, the fall of the Roman Empire did not erase knowledge entirely, but it altered cultural and technological trajectories. Similarly, an interstellar civilization might leave behind artifacts that weather into obscurity or become indistinguishable from natural formations over geological timescales. When we extend these concepts to the cosmos, we face the challenge of distinguishing between natural and artificial structures. A smooth, symmetrical object on a distant moon might be a natural boulder or a remnant of alien engineering. Detecting patterns that indicate purpose requires careful analysis and an openness to possibilities. Our search strategies must be attuned to anomalies in data rather than preconceived expectations. We may find that the first evidence of another civilization is a slight chemical imbalance, a geometric arrangement of rocks, or an unusual distribution of minerals. The Great Silence thus becomes a canvas for our imagination. It invites us to explore not only outer space, but also inner space, the space of ideas. Each proposed solution to the Fermi paradox reflects different assumptions about life, intelligence, and behavior. Whether we focus on improbable events, environmental requirements, growth dynamics, or social choices, we are ultimately grappling with the diversity of possibilities. Our own path is one among many. Other worlds may follow trajectories we have not yet conceived. Understanding our place in this context fosters empathy toward our own planet and its inhabitants. It reminds us that our struggles and triumphs occur on a tiny blue dot suspended in a vast void. The fragility of Earth's ecosystems, the preciousness of its water and air, and the interconnectedness of its living systems become more apparent when contrasted with the lifelessness of space. The realization that we may be alone, or that company is far away, intensifies the responsibility we bear to protect this haven. It also encourages us to cultivate curiosity and humility simultaneously. Curiosity drives us to build telescopes, launch probes, and decode signals. It fuels our desire to reach across the darkness. Humility tempers our expectations, reminding us that we may not find what we seek, and that our understanding is limited. The combination of these qualities allows us to explore with wonder while acknowledging uncertainty. In this balance lies the essence of scientific inquiry and the beauty of the human spirit. As we envision ancient civilizations closer to home, we begin to imagine the solar system as a stage for cosmic archaeology. The possibility that long-lost probes or structures might lie on the Moon, Mars, asteroids, or in the deep oceans of icy moons transforms familiar landscapes into potential sites of discovery. We will need new instruments and creative strategies to scan for anomalies. We will have to question our assumptions about what artifacts might look like after millions of years of erosion, impacts, and chemical alteration. Such a search will also require cooperation and care. The act of exploring for ancient artifacts cannot come at the expense of preserving pristine environments or contaminating potential habitats. International agreements, ethical frameworks, and technological safeguards will be necessary to balance curiosity with responsibility. The search for ancient neighbours is not only a scientific endeavour, it is a reflection of our values and our respect for the unknown. In anticipation of that exploration, we can draw inspiration from the philosophies and science of those who preceded us. Ancient astronomers, philosophers, and artists pondered the nature of the cosmos without modern instruments. They constructed myths, mathematical models, and stories that sought to place humanity within a larger tapestry. Today, we extend that tradition with satellites, telescopes, and computational simulations. The thread that connects us across time is the desire to know and to make sense of what we find. The silence of the cosmos, whether temporary or enduring, accentuates the importance of every voice we know. The songs of birds, the languages of people, the calls of whales. These are unique in the universe to our knowledge. Each species and culture contributes to a rich chorus of earthly life. Preserving this diversity is a form of cosmic heritage conservation. If we are alone, then we are the bearers of the universe's awareness of itself. If we are not alone, then our uniqueness adds to a grand symphony. As we close this segment of our journey, the echoes of equations, paradoxes, and filters linger. They remind us that certainty is elusive in a cosmos so vast. Yet they also illuminate pathways of inquiry. The numbers encourage us to refine our measurements. The paradoxes challenge our assumptions. The filters caution us about fragility. The sustainability perspective asks us to imagine different ways of being. Together, they create a framework within which we can explore, wonder, and prepare. Our next steps will bring us back to the familiar yet mysterious neighborhoods of our own solar system. There, we will look for signs of ancient visitors or indigenous technological species that may have arisen and faded long before humanity appeared. The stones of Mars, the icy shells of Europa and Enceladus, the craters of the Moon, all may hold clues. With patience and creativity, we will attempt to listen to what these worlds might whisper about the possibility that we are not the first to contemplate the stars. Before we pivot to that search, it is worth considering how our knowledge of exoplanets has expanded through different detection techniques. The radial velocity method measures the slight wobble of a star as orbiting planets tug on it, revealing the presence of unseen worlds. The transit method detects the dimming of starlight when a planet passes in front of its star from our perspective. Gravitational microlensing, direct imaging, and timing variations provide complementary ways to uncover planets at various distances and sizes. Each method opens a different window into the diversity of planetary systems. Transit surveys like Kepler and TESS have yielded a treasure trove of data. By monitoring the brightness of thousands of stars, these missions have identified planets ranging from tiny rocky bodies to bloated gas giants. Statistical analyses of transit data have revealed that small planets are more common than large ones, and that compact multi-planet systems are frequent. This suggests that the architecture of our solar system, with widely spaced planets, is but one of many configurations. Learning about these differences helps us refine our models of planet formation and migration. Radial velocity measurements complement transit discoveries by providing planet masses and orbital characteristics. Spectrographs attached to ground-based telescopes can detect velocity changes of a few meters per second, allowing astronomers to infer the presence of planets even when no transit occurs. Improvements in precision will soon enable the detection of Earth-mass planets in Earth-like orbits around nearby stars. When combined with transit data, radial velocity measurements allow us to determine planet densities, distinguishing between rocky worlds and those with thick atmospheres. Direct imaging of exoplanets is challenging because stars outshine their planets by many orders of magnitude. Coronagraphs and star shades suppress starlight, allowing faint planetary light to be detected. By observing infrared emissions and reflected light, scientists can characterize the atmospheres of giant planets and, in some cases, super-Earths. Future telescopes will push the boundaries further, enabling direct study of Earth-sized planets around nearby stars. These advancements will provide critical information about atmospheric composition, surface conditions, and potential biosignatures. Biosignatures are chemical or physical indicators of life. On Earth, life alters the atmosphere by producing gases like oxygen, methane, and nitrous oxide. If we detect a combination of gases out of equilibrium in an exoplanet's atmosphere, it could hint at biological processes. However, abiotic processes can also generate these gases, so context is crucial. Planetary temperature, stellar type, geological activity, and potential ocean coverage must all be considered when interpreting atmospheric signals. The search for biosignatures will require careful modeling and cross-disciplinary expertise. Technosignatures represent evidence of technology rather than biology. Examples include narrowband radio transmissions, laser pulses, industrial pollutants, artificial illumination, or megastructures. Detecting technosignatures would provide direct evidence of advanced civilizations. However, the range of possible technological activities is vast, and we have only just begun to define search parameters. Additionally, advanced societies may deliberately avoid detectable emissions or use communication modes we cannot yet sense. Thus, technosignature searches complement but do not replace biosignature investigations. Understanding how life arose on Earth can inform our expectations about other worlds. Early Earth was a hostile environment, bombarded by asteroids and bathed in ultraviolet radiation. Yet within this volatile cauldron, simple organic molecules formed. Whether life emerged in shallow ponds under cycles of drying and wetting, or in hydrothermal vents rich in minerals and energy, remains debated. The RNA world hypothesis suggests that ribonucleic acid could store information and catalyze reactions before the advent of DNA and proteins. If these pathways are plausible, they might occur elsewhere under similar conditions. Earth's early history also includes a violent event: the collision between the proto-Earth and a Mars-sized body that resulted in the formation of the Moon. This impact contributed to Earth's tilt, day length, and internal heating. It likely influenced the planet's geology, atmosphere, and potentially its habitability. Such giant impacts are common in young planetary systems, and their outcomes vary. Some collisions may sterilize a planet, others may deliver water and organics. Understanding these processes adds nuance to our assessment of habitability. The Great Oxygenation Event marked a profound shift. For billions of years, Earth's atmosphere was anoxic. Then, cyanobacteria began producing oxygen through photosynthesis, leading to oxidative weathering and the precipitation of iron formations. Eventually, oxygen accumulated in the atmosphere, enabling new metabolic pathways and paving the way for the evolution of complex multicellular organisms. This event may have been triggered by biological innovation and geological feedbacks. On other planets, the timing and magnitude of such transformations could vary dramatically, influencing the trajectory of life. The Cambrian explosion, another pivotal moment, saw an unprecedented diversification of life forms around 540 million years ago. The fossil record reveals a sudden appearance of a variety of complex body plans, many of which persist today. Possible causes include rising oxygen levels, changes in ocean chemistry, ecological interactions, and genetic innovations, like the development of Hox genes. If such bursts of complexity are contingent on specific environmental or genetic triggers, they may not occur universally. This adds another layer to the probability chain that leads to intelligent beings. From a philosophical standpoint, the anthropic principle reminds us that our observations are conditioned by our existence. We find ourselves on a planet conducive to life because only such planets can host observers. This selection bias complicates attempts to generalize from a single example. It does not imply that life is rare or common. Rather, it cautions against drawing sweeping conclusions from our unique circumstances. Recognizing this bias helps us interpret the Drake equation and the Fermi paradox with appropriate humility. Cosmic catastrophes like gamma-ray bursts, GRBS, and supernovae occur randomly across the universe. GRBs are extremely energetic events that can release as much energy in seconds as the Sun does over its entire lifetime. If such a burst occurs within a few thousand light years of a planet with life, it could strip away the atmosphere and cause mass extinctions. Supernovae also emit intense radiation and cosmic rays. The frequency of these events depends on galactic environment. Planets closer to star-forming regions may face higher risks. These hazards may periodically reset the evolutionary clock, influencing the emergence and survival of civilizations. The lifetimes of stars also play a role. Massive stars burn brightly and die young, leaving little time for life to develop on any planets they may host. Sun-like stars have stable lifespans of billions of years, providing a long window for evolution. Red dwarfs, the most common type of star, burn even longer, but can exhibit frequent flares and variation in luminosity. The interplay between stellar stability, spectral type, and planetary adaptation is complex. Life may thrive under conditions we consider inhospitable, but there are likely limits beyond which stability is insufficient for sustained evolution. Communication technologies may evolve beyond our current comprehension. While radio waves travel at the speed of light and penetrate interstellar space, they dissipate over distance and can be drowned out by cosmic noise. Lasers can send focused beams, but targeting specific locations across light years requires knowledge of where to aim. Alternative proposals include using neutrinos, gravitational waves, or quantum entanglement. Each presents technical challenges and theoretical uncertainties. If advanced civilizations adopt such methods, their messages may elude our receivers, adding to the impression of silence. The detectability of a civilization changes as its technology evolves. Early radio transmissions on Earth were broad and powerful, leaking into space and potentially detectable across light years. Over time, communications shifted to cable, fiber optics, and directional signals, reducing leakage. If our trend continues, Earth may become radio quiet from an external perspective. This suggests that even if civilizations broadcast signals at some point, this phase may be brief. Searching for fleeting transmissions requires continuous monitoring and sophisticated algorithms to distinguish artificial signals from natural phenomena. Our search programs reflect this challenge. Arrays of radio telescopes scan the sky for narrowband signals and transient bursts. Some initiatives harness the computing power of volunteers' computers to sift through data. Astronomers also use optical telescopes to look for short laser pulses. As instrumentation improves, we can observe more of the sky across more frequencies with greater sensitivity. Yet these efforts must contend with interference from human sources, such as satellites and terrestrial communications. Filtering out local noise while remaining open to unknown signal types is a delicate balance. Fast radio bursts, FRBS, illustrate the difficulty of interpretation. These are millisecond duration flashes of radio waves originating from distant galaxies. Their sources remain uncertain, with theories ranging from magnetars to exotic phenomena. A few fast radio bursts repeat, while most are singular. Although their properties are consistent with astrophysical origins, some have speculated whether they could be artificial. This speculation underscores the caution needed when encountering unfamiliar signals. Scientists must weigh natural explanations against the possibility of technosignatures, avoiding premature conclusions. Another line of investigation involves looking for spectral lines of artificial chemicals. Pollutants like chlorofluorocarbons or nitrogen trifluoride do not occur naturally in significant quantities. If detected in an exoplanet's atmosphere, they could indicate industrial activity. These molecules absorb light at specific wavelengths, leaving fingerprints in the spectra collected by telescopes. Detecting such signatures would require precise instruments and careful analysis to rule out natural sources. While challenging, this avenue broadens the scope of technosignature research. Light pollution on a global scale could also betray the presence of a technological species. Artificial illumination changes the brightness of a planet's night side. Sensitive observations could detect periodic variation in reflected light corresponding to day-night cycles, with the night side brighter than expected for a natural body. Studying the phases of exoplanets could reveal such anomalies. However, this approach assumes that an extraterrestrial civilization uses lighting similar to ours, and that their planet's rotation produces detectable modulation. Our own radio waves and light pollution remind us that we have been emitting signals into space for only a century or so. These signals travel at light speed, meaning that any civilization within about 100 light years could potentially detect them. Beyond that sphere, Earth remains invisible. The Milky Way spans more than 100,000 light years. Thus, our presence has barely begun to register on a galactic scale. Similarly, civilizations farther away may be broadcasting, but their signals have not yet reached us. In addition to physical artifacts and electromagnetic emissions, we can consider other forms of cosmic communication. Some have proposed that extraterrestrials might encode messages in genetic sequences or in the mathematical constants that underlie physics. While these ideas verge on the speculative, they highlight the creative range of possibilities. The challenge lies in discerning deliberate patterns from random noise. As in other areas of the search, openness to novel ideas must be balanced with rigorous analysis. Searching our own solar system for artifacts requires a multifaceted strategy. Regions of stability, like the Lagrange points where gravitational forces balance, could harbour long-term probes. Small bodies with low escape velocities are easier to land on and depart from, making them attractive for probes that wish to loiter. Trojan asteroids that share Earth's orbit may be particularly good hiding places. Examining these environments with telescopes, radar, and space missions could reveal subtle anomalies. A reflective patch on an asteroid, an unusual orbit, or a material with unexpected properties might warrant closer inspection. The surfaces of the Moon and Mars record impacts and environmental changes over billions of years. While erosion is limited on the Moon and slow on Mars, geological processes still occur. Any ancient artifact would need to withstand micrometeorite bombardment, radiation, and temperature extremes. It might be buried under regolith or disguised as natural rock. Ground-penetrating radar, high-resolution imagery, and in situ exploration could uncover structures or materials that do not match local geology. The search is akin to finding a needle in a cosmic haystack, but the potential reward is profound. Icy moons, like Europa and Enceladus, intrigue researchers, not only for their potential subsurface oceans, but also as possible locations for preserved materials. Ice can trap and protect objects from radiation and impacts. If a probe or sample was deposited in the ice long ago, it might remain intact. Exploring these worlds with landers and cryobots, machines designed to melt through ice, could reveal surprises. Even if we do not find artifacts, we may discover microbial life or organic chemistry that broadens our understanding of habitability. Comets and Kuiper belt objects offer additional storage for the past. Their cold, pristine surfaces could preserve traces of organic molecules delivered from interstellar space. Some scientists have speculated that life, or its precursors, might travel on comets, seeding planets. Whether or not this panspermia occurs, studying the outer solar system informs us about the ingredients available during planetary formation. It also reminds us that our search for life and technology extends beyond planets to a diverse array of small bodies. As we survey our neighbourhood, we must be careful not to impose anthropocentric expectations on what we might find. An artifact from an alien civilization could take forms we have not envisioned. It might be microscopic, integrated into the surface of a rock, or composed of materials unfamiliar to us. It could use quantum mechanical principles or biological systems as part of its functioning. Being open to unconventional possibilities is key, while avoiding the pitfalls of interpreting every anomaly as evidence of extraterrestrials. At the same time, skepticism is essential. Natural processes can produce features that seem artificial at first glance. Hexagonal columns in basaltic rock, spherical concretions, geometric crystal formations, and other patterns arise from physical and chemical laws. Distinguishing between natural and artificial requires careful context, comparative analysis, and sometimes multiple lines of evidence. The scientific method demands that extraordinary claims be supported by robust data. This discipline protects us from false positives and ensures that genuine discoveries stand on solid ground. The interplay between imagination and rigor is evident throughout the search for extraterrestrial intelligence. We must conceive of scenarios beyond our experience to recognize potential signals or artifacts. Yet we must also base our interpretations on empirical evidence and logical reasoning. This balance mirrors broader human endeavors, where creativity drives innovation and skepticism ensures reliability. Our exploration of the cosmos thus becomes a mirror for our intellectual virtues and vulnerabilities. Reflecting on cosmic distances further enhances our sense of perspective. Light travels about 9.5 trillion kilometers in a year. Even the nearest star system, Proxima Centauri, is more than 4 light-years away. At current spacecraft speeds, a journey to Proxima Centauri would take tens of thousands of years. The scale of space makes communication and travel arduous. Knowing this, we can appreciate the challenge any civilization would face in reaching or signaling another. Patience becomes a necessary virtue for cosmic neighbors. Timescales add another dimension. Human history spans a few thousand years. Earth has existed for 4.5 billion years. The universe is around 13.8 billion years old. Civilizations could rise and fall many times within these epochs. Geological and astronomical processes operate on timescales that dwarf human generations. Recognizing these spans reminds us that any momentary silence we perceive may not reflect a permanent absence, but a snapshot in a dynamic, evolving universe. In contemplating advanced civilizations, we often imagine beings with similar lifespans to ours. But extraterrestrials may have life cycles measured in centuries or minutes, depending on their biology or technology. They may be long-lived, slow thinkers, contemplating decisions over decades, or they may exist as digital minds, operating at speeds far beyond ours. These differences influence communication strategies and cultural evolution. A species that thinks slowly might consider our radio transmissions as flitting noise, while one that thinks quickly might find our responses frustratingly delayed. The possibility of post-biological civilizations adds another layer. Once a species masters digital consciousness, it might choose to upload into hardware or engineered substrates. Digital beings may not require planets or physical resources in the same way biological ones do. They could exist within asteroid habitats, in the cool outer regions of star systems, or even between stars, powered by cosmic rays and dark matter interactions. Their priorities and detectability might differ radically from those of flesh and blood organisms. If such entities exist, they may regard physical expansion as unnecessary. Their universe could be computational, exploring virtual worlds richer than any physical environment. Contacting other civilizations might be a lower priority than exploring the space of possible experiences. Or they might view communication as too risky, fearing hostile actors in a competitive universe. These speculative scenarios illustrate the diversity of potential motivations and caution us against assuming that all intelligent life shares our curiosity or sociability. Considering motivation also involves ethics. A civilization that values stewardship and non-interference might decide against revealing itself to younger species. It might prioritize the autonomy and natural development of nascent cultures. Conversely, a civilization with expansionist tendencies might colonize aggressively, seeking resources and power. The ethical frameworks of extraterrestrials, if they exist, could be as varied as those of humans. Understanding this range helps us frame potential interactions and anticipate the unexpected. Our own ethical choices shape how we search and how we might respond to contact. Debates about whether to actively broadcast messages into space, known as METI, messaging extraterrestrial intelligence, highlight differing views. Some argue that announcing ourselves could attract unwanted attention, while others believe it fosters openness and engagement. Developing protocols for contact, including how to verify signals, share information with the public, and coordinate responses, is an ongoing effort. These discussions demonstrate that the search for others is as much a social and political endeavor as it is scientific. Building on contact protocols, we must consider potential cultural impacts. Contact with an extraterrestrial intelligence could be transformative, affecting religion, philosophy, science, and daily life. The knowledge that we are not alone might inspire unity or provoke anxiety. Past encounters between human cultures show that exchanges can bring both enrichment and conflict. Preparing for such an event requires sensitivity to diverse perspectives and a commitment to transparency and inclusivity. Even without direct contact, the search itself influences culture. It inspires art, literature, music, and film, shaping how we imagine ourselves and others. Stories about aliens reflect our hopes and fears, projecting human qualities onto non-human forms. They serve as allegories for social issues and as mirrors for our values. Engaging with these narratives can enrich our understanding of the human condition and broaden our empathy. Educationally, the search for extraterrestrial intelligence sparks interest in science, technology, engineering, and mathematics. It encourages students to study astronomy, biology, chemistry, and computer science. It invites interdisciplinary collaboration between physicists, engineers, linguists, anthropologists, and ethicists. By pursuing this quest, we cultivate critical thinking, creativity, and cooperation, skills that benefit society, regardless of whether we find extraterrestrials. The search also advances technology. Building large telescopes, sensitive detectors, and powerful computers pushes the boundaries of engineering. Developing algorithms to process vast data sets contributes to machine learning and data science. Solving the challenges of deep space communication informs communications technology. These advances have applications far beyond astrobiology, improving medical imaging, environmental monitoring, and global connectivity. As we expand our technological capabilities, we also confront new risks. The same tools that enable exploration can be used for harm. Dual-use technologies like artificial intelligence and genetic engineering pose ethical dilemmas. Navigating these issues requires robust governance, international collaboration, and a shared commitment to the common good. The lessons we draw from contemplating the Great Filter may help us prioritize safety and foresight. Our journey through equations and paradoxes thus touches on every aspect of our relationship with the universe. It challenges us to think in scales of time, space, and complexity that stretch the mind. It invites us to view our planet with a mixture of wonder and responsibility. It calls on us to imagine possibilities beyond our immediate experience, while grounding our fantasies in scientific understanding. This interplay of imagination and reality is the heart of exploration. When we turn our gaze inward in the next segment, we will carry with us the weight of these reflections. We will examine the rocks, ice, and dust of our solar system, not as inert matter, but as pages in a cosmic history book. We will look for inscriptions from past visitors, whether they are natural patterns that tell the story of planetary formation or artifacts that hint at lost civilizations. In doing so, we will continue to balance curiosity with caution, skepticism with wonder, and humility with the boldness to ask, are we truly alone, or are there traces of ancient neighbours waiting to be found? The passage of time adds poignancy to our quest. In the brief span of human lifetimes, the stars seem fixed and unchanging. Yet over millions of years, they drift, die, and are born. Civilizations, if they arise elsewhere, may have blossomed and faded long before our species existed. Their messages, artifacts, or alterations to their environments would be fossils of minds long gone. Searching for such remnants teaches us to think beyond immediate gratification and to embrace a patience that spans eons. This patience is not passive. It is an active commitment to stewardship and learning. It requires building institutions and instruments that will outlast current generations, nurturing knowledge across centuries. The cathedrals of medieval Europe took generations to complete. Similarly, the observatories and missions we launch today may bear fruit in decades or longer. By embedding long-term thinking into our culture, we honor the continuity of human curiosity and prepare to participate in a cosmic story that unfolds slowly. As we stand on the threshold between contemplating equations and exploring landscapes, we sense a continuity. The numbers and paradoxes give context to our search, framing what is plausible and what is extraordinary. The rocks and ice will provide evidence to test our hypotheses and to spark new questions. Between the abstractions of probability and the concreteness of physical exploration lies the human spirit, weaving meaning from both. In the next chapter, we will step onto the surfaces of nearby worlds, carrying the insights gained from our deep dive into the odds, and listening closely for any signs that ancient intelligence once walked, rolled, or floated there. As the night stretches, our thoughts wander to the quiet spaces between stars, where emptiness echoes with possibility. We imagine that in those voids, civilizations may have risen and fallen, leaving behind only whispers in the cosmic background. The silence itself becomes a teacher, reminding us that absence can hold meaning as powerfully as presence. It encourages us to cultivate patience and sensitivity, to detect faint signals in noise, and to appreciate the subtle interplay between detection and interpretation.